My name is Arnold Wangakuramia, and in this full lecture of electrostatics for A-level physics, this is what you should expect. I'll be talking about what the atom is, charging by rubbing or by friction will be explained. We'll talk about charging by induction, why charged bodies attract neutral bodies, the electrophorus will be explained, the gold leaf electroscope, how we detect presence of charge, how we detect the magnitude of charge. We will describe Faradays Ice Pail experiment, the laws of electrostatics shall be talked about. That is all in the table of contents. Of course, we shall go ahead and talk about the lightning rod and how it works, and then the corona discharge and how that connects to the Van de Graaff generator. We'll talk about the electric field and draw the diagrams of the various electric field lines of various shapes. Coulombs law of electrostatics shall be explored together with its worked examples. Then we'll look at electric field intensity, how its definition and its worked examples as in calculations. Then we'll talk about Gauss theorem, the electric field potential, how the formula for electric field potential is derived, then as with worked examples as well. Then talk about potential difference formula together with its worked examples. We will talk about applications of electrostatics, things like how a photocopier works, things like fingerprint lifting, and so on. Then we'll talk about equipotential surfaces. Then we'll talk about capacitors, the formulas of capacitors in series, capacitors in parallel, worked examples of capacitors, charged capacitors, all these things. I encourage you to please share this full lecture with your fellow students. I believe that by the time you finish watching this lecture, you will have a strong command on this entire topic of electrostatics. If you feel there are some areas in this lecture, maybe you feel I need to do more worked examples, or I need to emphasize it more, or some area that is not clear, feel free to let me know in the comment section below. My name is Arnold Wangakuramia. This is Kisembo Academy, so let's get into the lecture. Electrostatics is simply a branch of physics that deals with the phenomenon and properties of stationary or slow-moving electric charges with no acceleration. As we explore this topic, we'll start with the atom. So what is an atom? An atom is simply the simplest invisible particle of an element. It consists of a nucleus, which is surrounded by electrons in their respective electron shells, as shown in the diagram. Here, we shall explore a few aspects about the atom. Thanks for tuning in. It's Kisembo Academy. So looking at this diagram, we have the nucleus, we have the electrons, and these electrons are positioned on electron shells. These electrons are free-moving. They are always rotating around this nucleus. In the nucleus, we have the neutrons and protons. These neutrons and protons combined together make the mass of the nucleus. It should also be known that the mass of an atom is concentrated at the nucleus, and these electrons have got a negligible mass. So when we want to find the mass of the atom, we simply compute the total number of neutrons and the total number of protons that are present in the nucleus. Now around the nucleus we have electron shells, and these electron shells have got free moving electrons that are always moving around. These free moving electrons are negatively charged. The protons that are found in the nucleus are positively charged, and the neutrons here do not have any charge. So the protons here are positively charged, the electrons are negatively charged, and the electrons are always free moving around the nucleus. In the first shell, the shell that is immediately after the nucleus, it has got a maximum of just 2 electrons, and in the next shells, the shells that come after the first one, have got a maximum of 8. When an atom is neutral, it means that the number of electrons that are rotating around this nucleus is equal to the number of protons that are inside. It means that the positives and negatives are the same. It means that that atom is considered neutral. Now, during bonding, these electrons that are always moving around the nucleus can be lost. Now, when an electron is lost during bonding, it means that the overall number of protons in the atom will be more than the overall number of electrons, it would mean that this atom has got more positive charges than negative. And so that means that overall, the atom will be considered a positively charged one. Likewise, during bonding, this atom can gain more electrons. When it gains more electrons, it means that we are having more negatives than positives. And so it means that overall, the atom will be considered negatively charged. Electrostatic electricity can be produced when you rub a plastic ruler or pen against hair sound, or when you iron a shirt, sometimes it produces a cracking sound. That is electrostatic electricity being produced. Also, when removing a sweater, for example, you hear a crackling sound. When you hear the crackling sound, sometimes when you're removing a sweater, it means that is static electricity being produced. To be able to identify positive and negative charges will depend on what we use. For example, if a polythene or ebonite rod are rubbed by a duster, they'll become negatively charged. And if a glass rod or cellulose acetate are rubbed by a duster, they'll become positively charged. In our next video, we shall look at how a body is charged by induction. Please don't forget to comment below or hit that like button. Someone out there may like to watch this tutorial. Don't forget to share. Otherwise, for more videos, simply subscribe to this channel. For Kisembo Academy, this is Arnold Rwangakuramya. Hello everyone, thanks for tuning in. So in today's video, we are simply going to discuss how we charge by friction or how we charge by rubbing. So these are two bodies right here, as you can see on your screen. Let me call this body A and let me call this body B. We are going to rub these two bodies, and I'm going to be able to explain how these two bodies get actually charged when they get rubbed. Now, before we go into the details, I would like us to take note that for every body, when the body is neutral, what that means is that it has the same positives as there are negatives. So from here we can see that it's having the same positives as there are negatives. Of course now, okay, the thing here is that, of course, we all know the structure of the atom. If I may draw something roughly here, if that is the atom, you know, it has a nucleus that is positive, then it has electrons that are always around the nucleus. And it is these electrons that are always continuously moving. I mean, if I'm to draw electrons here, these electrons are always moving. Well, I'm not going to go into all those details, just to make this this picture completely, simple. I'll just put it this way: that for a body that is, neutral, it means it has the same positives as the same amount of positives and negatives. The charges cancel themselves out, so it's relatively the same. That's what it means to be, neutral. Now, when we say that a body is positively charged, it doesn't mean that the body only has positive charges. No. It simply means that the body has more positives than negatives. The negatives are always there. The same is true when we say that a body is negatively charged. If a body is negatively charged, it simply means that there are more negative charges, or there are more electrons. There are more negatives than positives. That is, in other words, the net charge on the body is negative. That's what we mean. So this is exactly what happens. Now, when these two bodies rub each other, let me say they are going to rub each other like that. That is A rubbing and B rubbing with B. What happens is that now these bodies, their surface, there is such a thing we call work function. What is work function? Of course, work function is simply the minimum amount of energy that is required to get these electrons to move away from the surface of a body. Think about it this way.
if we are two individuals, and both of us are human beings who can easily get angry. Now, if I can come and slap this individual A, and that is individual B, if I can come and slap individual A, they can smile. If I come and slap individual B, they could get angry. So, if I come and slap individual A and then I slap individual B, but instead individual A smiles, but individual B, gets angry, it simply means that, the threshold of anger for individual B is much higher than that for individual A. What I'm trying to say is that it is easy to get individual B angry as compared to individual A. So consider the issue of getting angry and not getting angry as the work function. The amount of energy you need to get an electron from the surface of a body. So that's what the work function. So in other words, everybody has a certain amount of work function. So the body that has a lower work function will be able to release, electrons more than the other body. So when these two bodies start rubbing each other, the body that has a lower work function, in other words, one that can easily get angry, will release its electrons sooner than the other one. So when it releases its electrons, it means that these electrons are released and they move to the other body. So let's assume that body A in this case has a lower work function. So the electrons, the negative charges then, will move. Let me draw this again here. So what we're having here is that these bodies are now rubbing. So when they rub each other, like we are seeing here, there is rubbing going on here. As they rub each other, body A has a lower work function than body B. So body A, the one that has a lower work function, is going to lose its electrons to body B. Like that. So of course, it's not going to lose all its electrons, but some of the electrons in A will move to B. Remember, it's electrons that move. The positives don't move. It's the electrons that move. So when these electrons flow from body A to body B, what happens at the end is that you're going to remain with So from what you can see here, when these electrons drift from body A to body B, you'll find that this body A has more positive charges and this body B has more negatives. So because this body has more negatives than positives, then meaning that this body has a net negative charge. The same is true with this one, because now this one, it has lost electrons, so it has more positives than negatives, so this one has a net positive charge. So because as a result of that rubbing, you realize that body A has now a positive charge, body B has a net negative charge, and the two charges are equal but opposite in nature. So maybe just to give some examples of the bodies when they rub each other. What two bodies? For example, we can get a glass rod and rub it with a silk cloth. What happens when these two rub each other? When those two rub each other, a glass rod will turn out to be positively charged, and the seal cloth will turn out to be negatively charged. That's an example. Let's look at another scenario. Let's say another two bodies rub each other, ebonite rod and far. When ebonite rod rub each other with far, the far will definitely lose electrons, so the far will become positively charged and the ebonite rod will become negatively charged. Those are just some examples. And of course, this goes without saying. Please take note that when in our explanation here, when we are talking about work function, we are talking about the minimum energy that is required to remove an electron from its surface. That is work function, the minimum amount of energy we need to remove an electron from its surface. And of course, a body that has a lower work function means that an electron will be able to go off the surface easily. We shall explore more about work function when we are doing photoelectric effect.
How to charge a body by induction. The word induction is a combination of two words, an English word called induce and a Latin word called inductio. Combining them together gives you induction. Induction as a word has varying meanings depending on the context. For example, it could mean that the process of formally introducing you into an organization, or in medicine it could mean the process of bringing a child birth by artificial means, or in mathematics it could mean proving a theorem by showing that it is true, and so on. But for this video we'll look at induction in the physics context as simply the process of charging a neutral body by the proximity of another charged body, with the two not being in contact. This is what we mean by charging a body by induction. It's Kisembo Academy. Thanks for tuning in. In the first case, we get to see how to charge a body positively by induction. And in our first diagram, we are having a body that is negatively charged, and we are having a conductor. This conductor is placed on top of an insulator. So this insulated stand is holding a conductor. As you can see, this conductor has got both positive and negative charges, so this conductor is neutral. This is a negatively charged body. So we get a negatively charged body, we place it near a neutral conductor. When a negatively charged body is brought near this conductor, it means that this being negatively charged, it will repel the negative charges. And when these negative charges are repelled, the positive charges remain attracted here. The negative charges are repelled away. So while this conductor is still in the vicinity of this conductor, while this charged body is still in the vicinity of this conductor, we ground this conductor, or we earth the conductor. And when we earth the conductor, the negative charges are further repelled to the ground. So when we break the earthing, or when we break the ground, we remove this and that at the same time, you will find that most of the negative charges were repelled to the ground, so the conductor remains predominantly positive. It means that this has been positively charged by induction. Charging negatively by induction, we'll do it like before. When we get a positively charged body and we bring it in the proximity or in the vicinity of this neutral conductor, these positive charges are going to attract those negative charges. So the negative charges will be attracted to this side of the conductor, leaving this side with more positive charges. So while this body is still in the vicinity of the conductor, we earth the conductor. When we earth the conductor, negative charges are attracted from the earth into the conductor. When they are attracted to the earth into the conductor, you will find that this body now starts gaining more negative charges as compared to the positive charges that are already there. So when you break this earthing and remove this charged body all at once, you will find that you have gotten a body that is predominantly negatively charged, and this is how we charge a body negatively by induction. How to produce two opposite charges from one type of charge? We are going to get two conductors and we are going to make sure they are in contact. These two conductors are positioned on insulators. So when we put A and B conductors, we position them. This is end A and end B. We bring a positive charge, like before, we bring it in at the end, near end A. When we do so, these positive charges are going to attract the negative charges that are within these. Negative charges will be attracted towards end A, and so end B will have a net positive charge. When this happens, you separate these conductors while the charged body is still there. It's still in position. When you separate the two, you'll find that conductor B has a predominantly positive charge and A is negatively charged. And that is how we induce two opposite charges from using one type of charge. Now we should take note that in conductors, it is only negative charges that flow. Up next, we get to study about the electrophorus, a device that is used to produce an unlimited amount of charge. Please don't forget to comment below or hit that like button. Someone out there may like to watch this tutorial. Don't forget to share. Otherwise, for more videos, simply subscribe to this channel. For Kisembo Academy, this is Arnold Ranga Kuramia.
So why does a charged body attract a neutral body? We are going to explain this right now. So let's draw these two bodies. We have a charged body here. Let's say that this body is positively charged. By positively charged, it means that it has more positives than negatives. So I'm only going to indicate that only positives, but we all know that there are some negatives in this body, but only that this body is just having more positives than negatives. It has that. Then we have another body here that is neutral. Now, this body being neutral means that it has an equal amount of positives and negatives. So this is the neutral body. Let's call it body B. This is neutral and this is charged. So the question is that why does a charged body attract a neutral body? So now remember we have this law of electrostatics that like poles or like charges will repel and unlike charges will attract. So because like charges are going to repel each other and unlike charges will attract, when we bring this body closer to body B, when we bring this charged body to come closer to body B, what is going to happen is that these negative charges will be attracted towards this side. I mean, these negative charges will be attracted, the electrons. So when they are attracted, it means they are going to move closer to this surface right here. So when they move closer to that surface, it means that you are going to end up having an excess of negative charges on this side of this, of this body. So when this excess charge of negative charges on this side of the body, you'll find that these negatives have drifted from the back here. So it means that this side we have an excess of positives, and while this side we are having an excess of negatives. In other words, this neutral body now becomes polarized because we've brought a charged body near it. And since we all know that unlike charges attract, so that explains why, the attraction happens. Let me write this explanation briefly. Just to throw more light on this explanation right here, we are saying that when a charged body is brought closer to a neutral body, this is the charged body being brought closer to a neutral body, an opposite charge is induced on the near end. This is the opposite charge we are talking about that is being imposed on the near end. In this case, the charged body is a positive charge, so the opposite charge being induced on the near end is the negative charge, as you can see there. And so we continue to say that so we're saying that an opposite charge is induced on the near end of the neutral body. And a similar charge is induced at the far end of the neutral body. That similar charge we're talking about is this one. This is a positive charge. So another positive charge, or the similar charge we're talking about, is this positive charge that is induced at the far end of the neutral body, which is right there. So since that happens, then we go ahead to say that since opposite charges are closer, the attractive forces become greater than the repulsive forces. Now take note here that this is positive charge, this is negative charge. So you find that the positives and the negatives here create an electric field, and they are closer to each other than these, the positive charges here that are at the far end. The positive charges that are at the far end are being repelled by the positive charges here. And the distance between these positive charges and the positive charges at the far end is greater than the distance between the positive charges here and the negative charges right at this end. So since the opposite charges are closer to each other, then you're going to have a stronger force of attraction than that of, repulsion. So that's what we mean here when we say that since opposite charges are closer, attractive forces become greater than the repulsive forces, hence the attraction. And that explains why a charged body will always attract a neutral body. And that's it. My name is Arnold Kuramya, and this is Kisembo Academy. Take care.
An electrophorus is a manual capacitive generator, and as such is used to produce electrostatic charge by electrostatic induction. It has a metal disc and an insulating handle as shown in the diagram. In this video, we shall concentrate on how to charge the electrophorus by induction. It's Kisembo Academy, and thanks for tuning in. So looking at this electrophorus with an insulating handle and a metal disc, it has also we have a slab of ebonite or cellulose acetate. If we rub a slab of ebonite with a duster, it will become negatively charged, and if we place this metal disc on top of that slab, then it means the charge that is on that slab will be picked by that metal disc, and then we shall remove that metal disc with that charge, whether positive or negative, and we will be able to use it later. So in our write-up we have that when the slab of ebonite is rubbed with a duster, it becomes negatively charged, and so the metallic disc is placed on top of the slab. When we place that metal disc on top of the slab, it means that that slab is going to pick up that charge. This is the slab we are talking about. This is the metal disc. So after rubbing this slab with the duster, it will become negatively charged. When it becomes negatively charged, we get our metal disc and insulating handle. We place it on top of this slab. When we place it on top of this slab, remember that this metal disc initially was neutral, and so when you place it on top of this slab, this being negatively charged, it means that it's going to repel these negative charges. They will move away. The negative charges in blue will be repelled towards the top of the metal disc, and the positive charges will remain predominantly here. So, if we earth this metal disc, if we earth it or we ground it, it means that you're going to have these electrons flowing out of this metal disc into the earth. And so when we break this earthing and we remove this metal disc, you'll find that this will be predominantly positively charged. And in so doing, we will have charged this metal disc. In our next video, we get to look at the electroscope, a device that is used to detect charge. Please don't forget to comment below or hit that like button. Someone out there might like to watch this tutorial. Don't forget to share. Otherwise, for more videos, simply subscribe to this channel. For Kisembo Academy, this is Arnold Ranga Kuramia. The electroscope is a device that was used by early scientists to detect the presence of the magnitude of electric charge on a body. Back then, it was the first electrical measuring instrument. In this tutorial, we shall talk about the parts that make up the gold leaf electroscope and how it is charged, both positively and negatively by induction. This is Kisembo Academy. Thanks for tuning in. As you can see in this diagram, we are having the electroscope, or it is sometimes referred to as the gold leaf electroscope. It has got a brass cap. This brass cap is connected to a brass rod, which is connected to a brass plate, and this brass plate has got the gold leaf. This leaf keeps flapping, it keeps diverting, it keeps diverging upwards or converging towards the brass plate downwards, depending on what charge is imposed on top. This gold leaf or electroscope also has got an insulator, and we have a glass window there, and all this is within a metallic case. So now, what exactly is the use of this? This device called the electroscope can be used to detect the presence of charge, the nature of the charge, the magnitude of the charge, and the insulating property of any substance. We'll be looking at those later, but from our right up here, the device is used to detect the presence of charge, the nature of charge, the magnitude of the charge, and the insulating properties of a substance. A gold leaf electroscope, or an electroscope for that matter, can be charged in two ways. You can either charge it by contact or charge it by induction. In charging by contact, you simply place an electrophorus or any other charged body onto the cap of a gold leaf electroscope. Now, talking of an electrophorus, we did so in our previous videos. An electrophorus is simply a metallic disc that is mounted onto an insulating handle. So when we get this electrophorus and it is charged, when we put it on top of the cap of a gold leaf, the charge that is on that charged body simply is automatically transferred onto the electroscope, and that is how we charge by contact. So we will also explain how we charge a gold leaf by induction. We look at charging by induction negatively. How do we charge an electroscope negatively? If we want to charge an electroscope so that it attains a negative charge, it means that we are going to first introduce a body that is positively charged. We bring a positively charged body close to the cap of a gold leaf electroscope. This is the cap of a gold leaf electroscope. This is the brass rod, the brass plate, and the gold leaf. When we bring this positive charge, it means that it's going to attract the negative charges that are resident within this apparatus. So the negative charges will be attracted towards point A, and when the negative charges flow towards point A, it means that down here and around there, an excess of positive charges will be left. So it means that these areas will have an excess of positive charges as the negative charges are moving towards point A. Remember, as far as electrostatics is concerned, it is only the negative charges that move. Positive charges don't move. So this is our first step. We bring this positively charged body near the cap, and this is what happens. So when that happens, in the second case, we earth, while this body is still in position, we earth the cap of the gold leaf electroscope. So when we earth this cap, the electrons from the earth are going to flow. Remember, it's only electrons that flow, or the negative charges, not the positive ones. So the electrons will flow onto the cap. When they do flow, it means that we are going to have an excess of negative charges here. When these electrons flow into this cap, they are going to go ahead and neutralize the positive charges that are already here. So when these positive charges are neutralized, it means that the gold leaf electroscope here is going to collapse. When it collapses, we remove this, and the earthing at once. And when we do so, it means that now there is going to be a net negative charge in the gold leaf, and so this will cause this leaf to diverge once more. And that is how we charge a gold leaf electroscope negatively by induction. So how do we do it positively? In charging a gold leaf electroscope positively by induction, we are going to do more or less the same thing. We are going to introduce a negatively charged body, and we are going to bring it close to the cap of the gold leaf electroscope. When we bring it close, this negative, because this is negatively charged, it is going to repel the electrons, or it's going to repel the negative charges here. So you're going to find that there's going to be a predominant positive charges at A, more positive charges at A, and the negative charges that will have been here will have been repelled to point B and towards the leaf. And so just like we did before, we are going to earth this cap while this body is still in position. So while the negative charge is still in position, we are going to earth this cap, and when this cap is earthed, electrons are going to flow from the cap to the ground. So when the electrons go to the ground, it means that we are going to have less electrons here and more positive in this setup. And so after doing that for some time, when you remove this and that at once, you're going to have this predominantly having positive charges, and so this leaf will diverge. So that is how we charge a gold leaf electroscope positively by induction. So in summary, there are two ways an electroscope can be charged. It can either be charged by contact or by induction. In charging by contact, we do so by placing a charged body like a metal disc of an electrophorus on top of a cap of a gold leaf electroscope. This transfers the charge onto the metal disc onto the electroscope. In charging by induction, the procedures are more so similar onto how we charged a conductor by induction, as illustrated in the previous tutorials. The diagrams we have just explored show the process of charging the electroscope by induction. In our next tutorial, we shall look at how to use an electroscope to detect the presence of charge. Please don't forget to comment below or to hit that like button. Someone out there might like to watch this tutorial. Don't forget to share. Otherwise, for more videos, simply subscribe to this channel. For Kisembo Academy, this is Arnold Rwangakuramya. How to use an electroscope to detect the presence of charge. Like earlier said, we use an electroscope to detect the presence of charge on the body. This tutorial serves to show how this is done. This is Kisembo Academy, and thanks for tuning in. So we shall simply follow this table and we'll look at the observation and the sign of the charge that should be after making that observation. Let's look at this diagram here. This is the cap of a gold leaf electroscope. It's called the brass cap. This is the brass plate, the brass rod, the brass plate, and the gold leaf. This is a positively charged gold leaf electroscope. Now, let us introduce a body on top. If we introduced a body on top of this near the cap of this gold leaf electroscope, a positively charged body, what will happen? Because this is a positively charged body, it means that it is going to attract negative charges from down here up there. So when these negative charges are attracted to come up here, it means that there's going to be an excess of positive charges down there. And the excess of positive charges down here is what is going to cause an increase in divergence. And so it means that if we are having a positively charged gold leaf electroscope with this kind of divergence, then we introduce a body, and the observation is such that there is an increase in divergence, then it would mean that the body that will have been introduced will be the same charge as the gold leaf, which is positive. So that is what happens for the case of a positive charge. If we are having a negatively charged gold leaf electroscope and we attempted to introduce a body on top that is also negatively charged, what will happen? This negatively charged rod is going to repel negative charges that are on top here to come down here. So it means that the negative charges, upon being repelled, will create an excess of negative charges at the brass plate and at the gold leaf, and this will cause an increase in divergence. So that means that if you're having a negatively charged gold leaf electroscope like this one, and you introduced a body near the cap, and it is such that, and what happens, the observation is that there's an increase in divergence, then that would mean that the body that has been introduced at the cap of the gold leaf has got the same charge as the gold leaf electroscope, and that explains our first table. Our first table is saying that an increase in divergence, if that is the observation, it would mean that the sign of the charge of the body that has been introduced is the same as that on that electroscope. So now, let's examine the second case. At first, we are having a negatively charged gold leaf electroscope. So we introduce a body that is not negatively charged, but positively charged. What happens? When we introduce a positively charged body, these positive charges are going to attract the electrons from down here. So it means that the electrons that were formerly here are going to be attracted to come and concentrate up here by this positive charge. So when that happens, it would cause the divergence of this leaf to drop. And so what does that mean? It means that if you're having a negatively charged gold leaf electroscope, and you introduce a body whose charge you do not know on top, and the observation is such that the divergence of this gold leaf drops, it would mean that that body has got a positive. If the gold leaf is negative, it means the body is positively charged, like I have explained. Likewise, looking at a positively charged gold leaf electroscope, it is positively charged, the brass plate is positive, the gold leaf is also positively charged. But if you are to introduce a body at its top, a negatively charged body is introduced at its top, the divergence of this leaf is going to decrease. Why? Because when you introduce a negatively charged body at the top, the negative charges that are at the cap are going to be repelled away from this place. So they will be repelled towards the brass plate and the gold leaf. So since originally down here they were predominantly positive charges, when the negative charges that are on top are repelled downwards, they are going to neutralize the positives that are there. And when they are neutralized, it means that the divergence of that gold leaf will be decreased. So what does that mean? It means that if you're having a positively charged gold leaf electroscope and you introduce a body whose charge you do not know, and the observation you make is that the divergence decreases, then you just know that whatever body you have introduced there has got a sign or a charge whose sign is opposite the sign of the gold leaf electroscope, and that explains our second assertion, that a decrease in divergence means that the sign of the charge that is on top of the cap is the opposite sign as that on the electroscope. This brings us to the end of this video. Please don't forget to comment below or hit that like button. Someone out there may like to watch this tutorial. Don't forget to share. Otherwise, for more videos, simply subscribe to this channel. For Kisembo Academy, this is Arnold Rwangakuramya. Besides finding the nature of the charge of a body that is brought on the cap of a gold leaf electroscope, an electroscope can also be used to detect the magnitude of the charge. And detecting the magnitude of the charge is as simple as looking at the level of divergence of the gold leaf. If the gold leaf diverges very highly, it means that the magnitude of that charge is high. And if the divergence is not as much, it means that the magnitude is low. So in our write-up here, we are saying that here we compare the level of divergence. A higher divergence of the gold leaf shows a higher magnitude of charge. A gold leaf electroscope can also be used to compare the insulating properties of a substance. So, in our write-up here, we say that different substances are put on the cap of a gold leaf electroscope. When the divergence of the leaf falls, it shows a good conductor of electricity. And if there is no effect on the gold leaf, it shows a bad conductor of electricity. Please don't forget to comment below or hit that like button. Someone out there may like to watch this tutorial. Don't forget to share. Otherwise, for more videos, simply subscribe to this channel. For Kisembo Academy, this is an old Ranga Kuramya. Faraday's Ice Pail experiment. In Faraday's Ice Pail experiment will only show that there is no charge residing inside the hollow conductor. It's Kisembo Academy and thanks for tuning in. This is the gold leaf electroscope. It has got a cap, a brass rod, a brass plate, a gold leaf, a metal casing, and an insulator there. This is the apparatus. Now, to begin with the experiment, remember we said that we are carrying out this experiment to show that no charge resides inside the hollow conductor. So sphere B is put inside an ice pail, but while we put this sphere B inside this ice pail, we do not allow this sphere to touch the walls. We just leave it hanging. So now when we put this sphere and we leave it hanging in space, what exactly happens? Because this is a sphere that is positively charged, and then it is this setup is put on a gold leaf electroscope that is also positively charged. So what exactly happens when this sphere is in here? Now sphere B being positively charged is going to induce a negative charge around. Now this negative charge that has been induced inside the ice pail as a result of this positive charge is also going to induce a positive charge outside the ice pail. Of course, it can't induce a negative charge. It definitely has to induce the opposite charge. So the negative charge inside the ice pail induces a positive charge outside the ice pail. So outside the ice pail we have a positive charge that is induced all over. So now because of this positive charge that is induced outside the ice pail, this positive charge is going to attract electrons or negative charges from down here. And so negative charges are going to be attracted from the gold leaf, and they are going to come and concentrate more here on the cap, like as it is shown. So since electrons have been attracted, or negative charges have been attracted up there, it means that you're going to have more positive charges down here. And so because you're having more positive charges on the brass plate and at the gold leaf, this divergence will increase further. Why does it increase further? Because now the magnitude of the positive charges has increased. Remember, the laws of electrostatics state that like charges will repel. That's why they repel. But if these were unlike, they would attract. So that the divergence will increase. So now when this divergence increases, it simply shows that the charge outside this ice pail is actually the same as the charge that is on the electroscope, which is positive. We now let sphere B to touch the walls of the ice pail. When we let sphere B to touch on the walls of the ice pail, and then we later remove this sphere and we test for the charge, we will find that there is no more charge on sphere B. Initially we had put it in when it was positively charged, but when we let this sphere B when we let it touch the walls of the ice pail, then we remove it and test for the charge on B, we will find that B does not have any charge. Now why does that happen? It's no longer having a charge, but the divergence of the gold leaf is still remaining the same. So the question is that why is it that sphere B, which was initially charged, is no longer charged? And the only way you can explain this is that this is because when the sphere was allowed to touch the inside of the ice pail, the inducing charge outside the sphere, the inducing charge outside the sphere was neutralized by the induced charge inside the pail. This shows that the inducing charge outside the sphere and the induced charge inside the pail are equal in magnitude. Therefore, this proves to show that no charge resides inside a hollow conductor. And that's it for Faraday's Ice Pail experiment. Please do not forget to comment below or hit that like button. Someone out there might like to watch this tutorial. Don't forget to share. Otherwise, for more videos, simply subscribe to this channel. For Kisembo Academy, this is Arnold Rangakuramya. In this video, we'll discuss the law of electrostatics, insulators and conductors, the concept of the proof plane, and precautions we ought to take when carrying out electrostatic experiments. It's Kisembo Academy, and thanks for tuning in. First, we'll look at the law of electrostatics. It's as simple as that. It states that like charges repel and unlike charges attract. It means that if you have a positive charge and a positive charge, when you try to bring them together, they'll repel. Or if you have a negative charge and a negative charge, you try to bring them together, they'll repel. They'll resist to come together. But if you have a positive charge and a negative charge, when you bring them close, they'll attract each other. It is that simple. It is the same law that we use even with magnetism. So what are insulators? Insulators are simply materials that can't conduct electricity. And conductors are the reverse. These are materials which allow the flow of heat and electricity, and these insulators do not have free moving electrons. That's why they won't be able to conduct electricity or heat. Conductors have free moving electrons, and it is these electrons that are free moving that help in the conduction of electricity. What is a proof plane? This is simply a small metallic disc. A small metallic disc that is mounted on an insulating handle, and it is used to collect charges from conducting surfaces of different shapes. Now, how exactly does this work? Now, when we put this proof plane, or the metallic disc of a proof plane, in contact with a conducting surface of interest, the plane is then transferred onto an electroscope, which serves to show the magnitude of the charge by the deflection of the gold leaf. Therefore, this serves to show that a proof plane is used to tell the amount of charge at a point on a conducting surface. If we look at our diagrams here, we have a conductor here that is in that shape. We have a proof plane, and these are several proof planes being put on different points on that conductor. Now, from my earlier explanation, I just told you that you simply bring this proof plane, the proof plane, put it on the surface of this conductor, remove it, place it on the cap of a gold leaf electroscope, look at the deflection, and you're able to tell the magnitude of the charge. But if you look at this conductor here, we can say it is positively charged. But the positive charges, when you reach at this sharp point, there are more positive charges, they are more congested. It means that the charge density here is high, and when you go to these areas that are a bit flat, you see that there are less positive charges. It means that the charge density along these flat areas is low. But as you're coming towards the points, the charge density is high. There are more positive charges that are congested there. So you realize from this illustration that at sharp points, the charge density is high and it is low along places that are a bit flat or they are not exactly sharp. So this brings us to the next definition that we need to talk about. What exactly is surface charge density? Surface charge density is simply the amount of charge per unit area of the surface of the conductor. And because of very high surface density, it brings us to the action of sharp points. The action of sharp points is as a result of very high surface charge density. At sharp points, there is a very high charge density. This leads to high electric field around the sharp points, which ionizes the air molecules at the sharp points. This is the sharp point we are talking about. And now, because there is a very high surface charge density there, this is going to ionize the airs around here. And when the air around here is ionized, that is what we are calling the action of sharp points. Now, when a sharp-pointed conductor like this one causes ionization of the air molecules around it, the ions that are opposite this charge, in this case they will be negative. The ions that are opposite this charge, or that are opposite the sharp points, will be attracted towards the sharp point. Now, when they are attracted towards the sharp point, they neutralize this sharp point. Now, of course, when they neutralize this sharp point, it means that this sharp point is losing charge, right? Yes. So now, this apparent loss of charge by the conductor is what we call corona discharge. I'll say that again. When a sharp-pointed conductor causes ionization of the air molecules around it, ions that are opposite are attracted towards the sharp point, and those ions neutralize it. So this apparent loss of charge by the conductor is what we call corona discharge. So let's look at the precautions that we take when carrying out electrostatic experiments. When we are carrying out electrostatic experiments, fire should be kept away from the apparatus, since fire produces ions which can discharge the bodies. Also, experiments ought to be carried out in dry environments, because damp environments have moisture which carries ions that can discharge the bodies. Up next, we'll look at the application of corona discharge, and in particular, we'll discuss how a lightning conductor works. Please don't forget to comment below or hit that like button. Someone out there might like to watch this tutorial. Don't forget to share. Otherwise, for more videos, simply subscribe to this channel. For Kisembo Academy, this is Arnold Ranga Kuramya. We have all experienced lightning and thunder. Lightning comes first, then thunder is heard later, since light travels faster than sound. I'm sure we've all heard, probably over the news or physically, how lightning sometimes destroys buildings and trees, sometimes causing death to people that especially take shelter under the trees when it is raining. To protect a building from the disasters caused by lightning, a device called a lightning conductor or a lightning rod is normally placed at the highest point of a building. This device was invented by an early scientist called Benjamin Franklin, the very reason why it is sometimes referred to as the Franklin rod. In this tutorial, we shall discuss how this lightning conductor or how this lightning rod works. It's Kisembo Academy, and thanks for tuning in. First, we need to ask ourselves, how does lightning occur? Now, during a storm, the clouds move fast, and as a result, rub against each other and against air. This rubbing makes them to acquire charge. This charge is normally distributed on a cloud in such a way that the top part is positively charged and the bottom part is negatively charged. Lightning occurs when a certain electrostatic discharge occurs between two electrically charged regions of the cloud, or between charged clouds, or between a cloud and the ground. In other words, when two oppositely charged clouds get to be near each other, a huge spark of electrons jumps from the negatively charged cloud to the positively charged cloud. It can happen between two clouds. It can happen within a cloud, because this part is positive and that's negative, so the spark happens between the cloud, or it can happen between the cloud and the ground. This spark generates a lot of heat, which warms up the air around, causing it to rise. When the air rises, air from the neighboring layers reaches to the spot to replace the risen air, and in so doing, a loud sound is produced. This loud sound is what we call thunder. So now, when all this happens, how does the lightning conductor work? Here we have a lightning conductor, a schematic diagram. In this diagram, we're having copper spikes that are connected to a copper strip, and this copper strip at the bottom is a copper plate. It is more so like this. This is a lightning conductor with the copper spikes. It is connected to a copper rod which goes along the building, and it is buried into the ground. So what exactly happens here? How does the lightning conductor work? These are the spikes. When a negatively charged cloud comes near the spikes, a very high positive charge is induced at the spikes. This creates a very high electric field around the spikes. Now, the very high electric field around the spikes, it causes the ionization of air around the spikes. So when the air around the spikes gets ionized, you're going to have positive ions in the air will be repelled towards the cloud, and in so doing, they will be discharging the cloud. The negative electrons are attracted to the spikes. As a result, the electrons from the cloud are safely conducted to the ground, and this prevents lightning from striking the building. This brings us to the end of this video. Please don't forget to comment below or hit that like button. Someone out there may like to watch this tutorial. Don't forget to share. Otherwise, for more videos, simply subscribe to this channel. For Kisembo Academy, this is Arnold Ranga Kuramia.
So in this session, I'm going to talk about the corona discharge and the Van de Graaff generator. Now, if I may draw a simple diagram here, this is something that we have explored before. If we are having this being a conductor, if we are to illustrate the charge distribution on this conductor, let's say there are positive charges on this conductor, you'll realize that on the flat surfaces or the surfaces whose curvature is low, there's space between the charges, as you can see, that the charges are not so crowded. But as we get to the point where the curvature is quite small, then we have a concentration of charge. So what does that mean? Now that means that the charge density in these areas that are a bit flat, the charge density is low, and because of the overcrowding of these charges or the positive charges, as we are coming to this sharp point or to this area where the curvature is quite high, the charge density is high. So here we are having a higher charge density. So we are having a higher charge density there as compared to these other surfaces that are flat. Now, because of this higher charge density, the air around this place is going to be more intense. In other words, there is more electric field intensity. So as a result of this higher charge density, there is a higher or more intense electric field intensity around the sharp point. So because there is that kind of scenario, the air molecules around this sharp point are going to get ionized. And as they are ionized, since this is now, for example, this is positively charged, it means that the negative ions around this sharp point are going to be attracted towards the positive charge. When these negative ions are attracted towards the positive point, because unlike charges attract, these positives will be repelling away the positive ions. So in other words, the positive ions are repelled away while the negative ions are attracted towards this point charge. So when these negative ions are attracted towards this positive charge, they are going to go ahead and discharge it. So this positive point that is highly positive, because it is having a very high curvature, it will be neutralized by these negative ions that are attracted towards it, while at the same time we are having positive ions that are being repelled away. So we have some sort of electrical wind right there. So when this happens, this whole scenario of these electrons being attracted towards this positive sharp point and discharging this sharp point, that now is what we call corona discharge. So this concept of corona discharge is applied in what we call the Van de Graaff generator. And so now let's talk about how this corona discharge phenomenon works in the Van de Graaff generator.
The year 1929, American physicist Robert J. Van de Graaff gave a solution by designing a machine which collects static charges and produces a large amount of electrostatic potential difference up to 10 power 7 volts. This Van de Graaff generator works on two principles: electrostatic induction and action of points. Electrostatic induction is a process of generating static electricity in a material without touching it. The electric charges on the surface of a charged object do not necessarily spread out evenly. They accumulate more at the sharper areas than at flatter areas. The leakage of electric charges from the sharp points of the charged conductor is known as action of points. Now let us see the construction of Van de Graaff generator. A large hollow spherical conductor A is fixed on the insulating stand. A pulley B is mounted at the center of the hollow sphere and another pulley C is fixed at the bottom. A belt made up of insulating materials like silk or rubber runs over both pulleys. The pulley C is driven continuously by the electric motor. Two comb-shaped metallic conductors D and E are fixed near the pulleys. The lower comb D is maintained at a positive potential of 10 power 4 volt by a power supply. The upper comb is connected to the inner side of a hollow metallic sphere. Working of a Van de Graaff generator. There is high electric field near the comb D, so air between the belt and comb D gets ionized due to the action of points. The positive charges are pushed towards the belt and the negative charges are attracted towards the comb D. The positive charges are stick to the belt and they move up. When the positive charges are reached to the comb E, because of the electrostatic induction, comb E acquires negative charge and sphere acquires positive charge. The acquired positive charge are distributed on the outer surface of the hollow sphere. At the same time, the negative charges produced due to the corona discharge nullify the positive charges in the belt before it passes over the pulley. When the belt descends, it has almost no net charge. At the bottom, it again gains large positive charge. The belt goes up and delivers the positive charge to the outer surface of the sphere. This process continues until the outer surface produces the potential difference of the order 10 power 7 volt, which is the limiting value. We cannot store charges beyond this limit since the extra charges start leaking to the surroundings due to the ionization of air. The leakage of charges can be reduced by enclosing the machine in a gas-filled steel chamber at very high pressure. The high voltage produced in Van de Graaff generator is used to accelerate positive ions for the nuclear disintegration and other applications.
The electric field. What exactly is an electric field? It is simply a region around an electric charge where an electric force can be experienced. And as you can see, an electric field is always represented by lines of force. Now, these lines of force have got a direction, and by definition, the direction of an electric field at a point is simply the direction in which a small positive charge would move under the influence of the field if it was placed at that point. So it means that if this is a positive charge and we placed a small positive charge, if this is positively charged, and we placed a small positive charge here, it will move in that direction because we said like poles repel, and then like charges repel, and unlike charges attract. So if this is a positive one and that's a positive charge, like a positive charge placed here will move in that direction. It will move away from the positive charge. But if we put that positive charge here, and this is negatively charged, that positive charge will move in that direction. And that is how we defined our direction of field. So the direction of field will always move away from the positive and towards the negative. These directions or these electric fields have got lines of force. The arrows on the lines of force show directions of the force on a positive charge, and the force on a negative charge will always move in the opposite direction. So here we have like charges, the positive and the positive. They are having the same kinds of electric fields, and because from the law of electrostatics, like charges repel, and as a result we have point X, which we are calling the neutral point, and at that point the electronic field strength at that point is, the resultant force at that point is 0. Unlike charges will attract, and because they do attract, their field lines merge as seen. This is a positive and that's a negative. We also have illustrations for lines of force for two plates, electric plates. This plate is positively charged and that is negatively charged. The lines of force will move from the positive towards the negative. The electric field lines will be such that they will move from the positive plate to the point charge, which is negative, as illustrated in the diagram. This brings us to the end of this video. Please don't forget to comment below or hit that like button. Someone out there might like to watch this tutorial. Don't forget to share. Otherwise, for more videos, simply subscribe to this channel. For Kisembo Academy, this is Arnold Rangakurami. Coulombs law of electrostatics. It simply states that the force between 2 point charges is directly proportional to the magnitude of the product of the charges, and it is inversely proportional to the square of the distance between them, or to the square of their separation. Let's assume we have 2 point charges. We label them Q1 and Q2. Those are 2 point charges. These 2 point charges are separated between them by a distance. We are going to call the distance of separation R. So according to the law, it says that the force that exists between these 2 point charges, which we shall call force F, is going to be directly proportional to the product of these 2 charges. It means it's going to be directly proportional to Q1 times Q2, but also it is inversely proportional to the square of their distances apart. So it is directly proportional to the product of the charges and also inversely proportional to the square of the distances apart. So for us to remove this proportionality sign, we are supposed to introduce a constant of proportionality, which we shall call K, and in this case it will become F is going to be equal to K times Q1 Q2 over R squared. From experimental observations, the value of K is equivalent to 9 times 10 to the power 9, which is also equal to 1 over 4 pi epsilon naught. Epsilon naught simply stands for the permittivity of free space, or the permittivity of a vacuum. This is going to be 9 times 10 to the power 9 from experimental observations. And so it means that our formula for the force that exists between 2 point charges is going to be F. This brings us to the end of this video. Thank you for tuning in. Please don't forget to comment below or hit that like button. Someone out there might like to watch this tutorial. Don't forget to share. Otherwise, for more videos, simply subscribe to this channel. For Kisembo Academy, this is Arnold Rangakurami. We have a question here. Find the force between 2 point charges. We have positive 4 microcoulombs and negative 3 microcoulombs, and these 2 point charges are placed 10 meters apart in air. So let's try and draw a sketch of this. We have, let's call this Q1. We have that Q2. It's another point charge. This is negative 3 microcoulombs. Micro means times 10 to the power negative 6. And we have here negative 4, positive 4. microcoulombs, and these 2-point charges are separated by 10 centimeters. And now we are required to find the force between those two charges. So what is the force due to Q1? We know that our formula from our previous video, our formula F is going to be equal to Q1 Q2 over 4 pi epsilon naught. Epsilon naught is the permittivity of air, but we know that 1 over 4 pi epsilon naught from experimental observations is equivalent to 9 times 10 to the power 9. So it means that our formula there, F, is going to be equal to Q1 Q2 over this is times r squared, right? Times r squared, multiply that by 9 times 10 to the power 9, like that. So this is our formula, the formula we're going to use. So to go back, the force that exists there, our force is going to be Q1. Q1 will be that 3 times 10 to the power negative 6. It's times 10 to the power negative 6 because it is microcoulombs. So it's 3 times 10 to the power negative 6. Multiply that by Q2. Q2 is 4 times 10 to the power negative 6. And multiply that by times 9 times 10 to the power 9. Divide all that by the square of the separation. We are supposed to convert this, supposed to be in meters. So this is 10 centimeters, converting that to meters is 0.1 meters. So divide that by 0.1 squared. And the force we shall get here will be 1.08 times 10 newtons. And this kind of force will be an attractive one. Why? Because according to the law of electrostatics, we said that like charges attract, unlike charges attract, and like charges repel. This is a negative, that's a positive. It means that the force that exists between here is an attractive force of 1.08 times 10 newtons. We are being required to find the resultant on charge B. Now, charge B is in between charge A and charge C. Charge A is negative 3 microcoulombs and charge C is negative 7 microcoulombs. Now, let's put this at the back of our minds, the law of electrostatics. It says that unlike charges attract and like charges repel. Now, if we are to find the resultant force on this B, we know that this charge B is experiencing forces due to two charges. It is experiencing a force due to charge A, and it is also experiencing a force due to charge B. Now, if we are to examine the force due to charge A, we know that this is a negatively charged point and this is positively charged. And since these two are charges that are negatively charged, they are of different charges, negative and positive, it means there's going to be a force of attraction in between here. So it means that charge B is going to be attracted towards that side. Likewise, if we look at charge C is negatively charged, B is positively charged. It means that B is also being pulled in the direction towards C because there is a force of attraction in between there. So what does that mean? It means that if this is B, if that is B, it is experiencing a force due to C in that direction, a force of attraction towards C, and it is also experiencing a force of attraction due to charge A. And now our job is to find the resultant due to these two forces. So we shall first find force due to A, get force due to C, and then we find the resultant by subtracting. The greater force is the one that takes the day. So let's find the force due to A, the force of attraction due to A. The force of attraction due to A is going to be equal to, let's begin by, it is going to be QA times QB over 4 pi epsilon naught. But like we said before, 1 over 4 pi epsilon naught is the same as 9 times 10 to the power 9. So it means that this is going to become equal to 9 times 10 to the power 9. Multiply that by QA. What is QA? The charge is going to be 3 times 10 to the power negative 6. Multiply that by the charge on B, which is 4 times 10 to the power negative 6. All that divided by r squared. The distance of separation between A and B is 10 centimeters. When we convert that to meters, it's going to become 0.1 squared. And our answer there will be, it is going to be 1.08 times 10 to the power 1 newtons. So now that is the force of attraction due to charge A. So it means that charge A is attracting B by a force of 1.08 times 10 to the power 1 newtons in that direction. So now let's find the force of attraction that is due to C in that direction. So the force due to C, Fc, is going to be equal to QA, that's the charge due to B, QB and QC. So it is QB and QC over 4 pi epsilon naught. So that's going to become 9 times 10 to the power 9. 9 times 10 to the power 9 is the 1 over 4 pi epsilon naught times r squared. 9 times 10 to the power 9, multiply that by QB. B is 4 times 10, it is 4 microcoulombs. So it is 4 times 10 to the power negative 6. Multiply that by QC. QC is 7 microcoulombs. So multiply that by 7 times 10 to the power negative 6. All that is divided by r squared. The distance between B and C is 10 centimeters. Converting this to meters is going to be 0.1 meters, so it will become 0.1 squared. And our answer here for Fc is going to become 10.08 times 10 to the power 1 newtons. So we are having our particle now B. Our particle B is experiencing a force in that direction of 10.08 times 10 to the power 1 newtons. That is force due to particle C. And it is also experiencing a force due to particle A, which we already got as 1.08 times 10 to the power 1. So to find the resultant force F is simply going to be the larger force, which is Fc, minus the smaller one, which is Fa. It is going to be 10.08 times 10 to the power 1 minus 1.08 times 10 to the power 1. Our resultant force will be 9 times 10 to the power 1 newtons, and this is towards charge C. In the figure below, two small equal charges, 2 times 10 to the power negative 8 coulombs, are placed at point A and point B. One of them is positive and the other is negative. FB is 6 centimeters. That is the distance between A and B. Find the force on a charge that is 1.0 times 10 to the power 8 coulombs. On a charge 1.8 times 10 to the power negative 8 coulombs that is placed at P, where P is 4 centimeters from the line FB, along the perpendicular bisector XP. We have a diagram here that tries to summarize this question. It's a bit long. They are talking about two charges that are equal but opposite. These are the ones at A and B. We have positive 2 times 10 to the power negative 8 and negative 2 times 10 to the power negative 8. They are 6 centimeters apart, and we are having a charge P, which is 1.0 times 10 to the power negative 8 coulombs, and it is 4 centimeters from the perpendicular bisector XP. This diagram serves to summarize this whole question. And the question is asking us, they're asking us to find the force that is being imposed on that charge P. Now, if you look at that charge P, the charge P has got two forces that are acting on it. First of all, P is positively charged, but it is experiencing a force due to A, and it is also experiencing a force due to B. Now, what kind of force is being experienced by P due to A? This being positive and this being also a positive charge, it means that there is a repulsive force in between here. So it means that due to A, the force on P will be acting along that direction. It will be repelling it away from here in a straight line. Looking at charge B and P, B is a negative charge, and P is a positive charge. Since these two charges are opposite, it means that there is a force of attraction. So it means that as far as B and P is concerned, the force acting on P will be working in that direction along the straight line towards point P. So if we were to redraw this diagram to show the forces that are acting on P, this is how it would be. It would mean that charge P in that same straight line, if you had to consider that straight line and this straight line, it would mean that the force acting on P due to A is repelling that P. It is pushing it away, so it will be acting in that direction. And the force acting on B due to P will be attracting, so it is in that direction. Why is that? Unlike charges attract and like charges repel. And if, according to our question, this B is negative, this is positive. That's why there is an attraction here. This P is coming that way. And between A and P, this is positive. This is also positive. So that there's a force of repulsion. This is being pushed away. So you find that charge P is experiencing two forces. Having charge, we are having a force due to A, and here we are having a force due to B. So it means overall, if we are to isolate charge P, it comes out like this. There is a force due to A, there is a force due to charge B. This is inclined at an angle to the horizontal. Let's call that angle theta, and let's also call this also theta. So finding the resultant force due to P, it means that you're supposed to resolve the forces due to this point, both horizontally and vertically. We resolve forces due to that point, and after resolving those forces, we're able to find the resultant force that is acting on that point P. If we are to look at this triangle, we could draw a parallel line here going through this point. This line is parallel to this line. So if we are to get this angle theta there, this angle is the same as that angle down here. So these are called Z alternate angles. So if this is an angle theta, that's an angle theta. This here is having 4 centimeters there. We have 3 centimeters this way, 3 centimeters that way. It means for us to find the length of this hypotenuse, it is going to be 4 squared. We use Pythagoras theorem. So it's going to be 4 squared plus 3 squared is going to give us x squared, and this value of x is 5. So this is going to be 5 squared, 5 centimeters. It's the same story in this other triangle. 4 squared plus 3 squared will give us 5 squared, 5 centimeters. So it means that this is 5 centimeters, that's 5 centimeters, that whole thing is, this makes it an isosceles triangle. And if this is the value of theta, one thing about isosceles triangles is that the base angles are the same. So meaning that if this is angle theta, it means that this angle here is also theta. If that angle is also theta, it means that looking at this theta, we said this is theta, this angle is equal to that, because these are alternate angles. These are two parallel lines, and that angle is the same as that, according to our angle properties. And then since this line is parallel to this one, this angle is also equal to that angle, because this theta and that is also theta, because they are corresponding angles here and there from our angle properties. So it means that if we are to isolate this charge like we have done here, and this is angle theta, it means that this angle down here is also theta. It simply means that these two angles are the same, no difference. Okay, so now in resolving forces, it means that we are going to resolve this angle, the force FA, along the horizontal and along the vertical, along the x-axis and along the y-axis. We are also going to resolve this force along the x-axis and along the y-axis, and then we shall eventually find the resultant of the two forces. So we begin. When we are to resolve these forces, it would mean that resolving it along the y-axis is going to be FA. We are looking at FA. Resolving it in the y-axis, it would mean it is FA sine theta. Then resolving for FA is going to be FA sine theta. Then resolving FB along the y-axis is going to be minus FB sine theta. Because resolving this along the y-axis, we are looking at this. Then resolving the force along the x-axis, the two forces along the x-axis, looking at FA, resolving it along the x-axis is going to be FA, the cosine of that angle, theta, plus FB, resolving it along this is going to be FB cos of theta, giving us R2. So if we get R1 and R2, then we will be able to resolve those two to find the resultant of the force on that particle. But you do not have FA and you don't have FB. So we first find the FAs and FB. Now remember, for us to get FA, it's a repulsive force that is between P and A. For us to get FB, FB is an attractive force between P and B. So we are going to use our formula, the one we used when we are trying to calculate Coulombs law. When we are trying to illustrate Coulombs law. And that is that for FA is going to be the charge on A times the charge on B. It's the product of the charges, and divide that by the distance, their mean distance, their separation squared. So QA is going to be 2 times 10 to the power negative 8, which is the charge on A is 2 times 10 to the power negative 8. The charge on P is 1 times 10 to the power negative 8. Multiply that by 9 times 10 to the power 9. This is equivalent to 1 over 4 pi epsilon naught. Divide that by the separation squared. Their separation is 5 centimeters, but it's supposed to be in meters, which is 0.05, and it's supposed to be squared. And that's how we end up with 0.05 squared. And we get our force as 7.2 times 10 to the power negative 4 newtons. So that is 7.2 times 10 to the power negative 4 newtons. So now let's try and find FB. FB, the force that is acting on P due to B, we get this using the same formula. Q, the charge on B times the charge on P. Divide that by 4 pi epsilon naught times R squared. The charge on QB is 2 times 10 to the power negative 8 times the charge on P, which is 1 times 10 to the power negative 8 times this 9 times 10 to the power negative 9, which is equivalent to 1 over 4 pi epsilon naught times the separation. Now the separation between P and B, this is 5 centimeters like we had earlier found out, and converting that to meters is going to be 0.05, and if we square that, it will be 0.05 squared. Our answer will still be the same as this, 7.2 times 10 to the power negative 4 newtons. So now we are having two forces here. We are having FA acting in that direction, and it is identical to the force FB acting in this direction, acting on that point P. So now we find the resultant of these two forces, the resultant acting on that. So getting our value of R1 means we're going to substitute for the values of FA and FB, which we have gotten. Sine theta, our values of theta here are the same all throughout. So to get theta here, sine theta there is simply opposite, which is 4, over hypotenuse, which is 5. And then our cosine of theta is going to be equal to adjacent, which is 3, over hypotenuse, which is 5, 3 over 5. So we simply come and substitute in here. So resolving along the y-axis is going to be FA times the sine of theta, which is that, minus FB, which we have gotten, times sine theta, which is that, to give us R1. And from our computations, resolving along the y-axis, our value of R1 is 0. When we resolve along the x-axis, our value of R2 is going to be 8.6 times 10 to the power negative 4 newtons. So at the end of the day, we have something like this. We have that our resultant force in the y direction is going to be 0 newtons, and the resultant force in the x direction is 8.6. If this R1 had a value like 5, say, we would go ahead to find the resultant by using the Pythagoras theorem. It would be the square root of the square of that and the square of that combined. But since R1 is 0, it means that the resultant is going to be R2, and it's in the direction of the positive x-axis. So our answer is that the resultant force that is being experienced there is 8.64 times 10 to the power negative 4, and it is happening in the positive x-axis. This brings us to the end of this video. Please don't forget to comment below or hit that like button. Someone out there may like to watch this tutorial. Don't forget to share. Otherwise, for more videos, simply subscribe to this channel. For Kisembo Academy, this is Arnold Rwanga. In this question, we are being asked to find the resultant on force Q3. This is force Q3, and we are being asked to find the resultant on this force, on this charge. Now, this charge is experiencing forces due to Q2, due to Q1, and due to Q4. Force Q3 is a positive, charge Q3 is a positive one, charge Q2 is a negative one. Since unlike charges attract, it means that the force of Q3 due to Q2 will be in that direction, because these two are attract. So if this force is to be stationary, this force will be pulled in that direction. The force due to Q2 will be pulling this in this direction. The force due to Q1 will be pulling Q3 away, because this is positive, that is positive, and since like charges repel, it means they will be parting separate ways. So this will be moving in this direction. And then we have charge Q4. Charge Q4 is also positive. Q3 is also positive. It means along this line, the force due to Q4 will be pushing this downwards. And so with that kind of analysis, we'll end up with the forces on Q3 in these kinds of direction like this. We have force due to Q2 in that direction. We have force due to Q4 moving downwards. And then we have this in this direction, force due to Q1. So our task is very simple. We are going to find these forces FQ1, FQ4, and FQ2. After finding those forces using Coulomb's law of electrostatics, then we shall find the resultant of these forces, and that will be the resultant force acting on charge Q3. We'll begin finding the force due to Q1. The force acting on Q3 due to Q1, it means we are considering this and that. The charge on Q1 is 2 microcoulombs, the charge on Q3 is 5 microcoulombs. So we begin. FQ1 is going to be equal to Q1 times Q3 divided by 4 pi epsilon naught times r squared. That's going to be, what is Q1? Remember, 1 over 4 pi epsilon naught is 9 times 10 to the power 9. Multiply that by Q1. Q1, if we look here, Q1 is 2 microcoulombs. So it means that our Q1 is 2 microcoulombs. 2 times 10 to the power negative 6. Multiply that by Q3. Our Q3 is 5 microcoulombs. So it is by 5 times 10 to the power negative 6. Divide all this by their separation squared. What is the distance between them? The distance between Q3 and Q1 is 5 centimeters. Converting this to meters is going to be 0.05 meters. So this squared, this is going to give us 0.05 squared. And our force FQ1 is going to become 36 newtons. So we find force acting on Q3 due to Q4. So FQ4 is simply going to be equal to Q3 Q4 over 4 pi epsilon naught r squared. R is the distance between the two charges. That is simply going to become 9 times 10 to the power 9. We said 9 times 10 to the power 9 according to experimental observations is what is equivalent to 1 over 4 pi epsilon naught. Multiply that by Q3. We say, you know that Q3 is 5 microcoulombs and Q4 1 microcoulomb. So continue with our calculation. It's going to be times Q3, which is 5 times 10 to the power negative 6, times Q4, which is 1 microcoulomb, so it's 1 times 10 to the power negative 6. Divide all that by the distance between them. If you look at our diagram, the distance between Q3 and Q1 is 3 centimeters. Converting this to meters is going to be 0.03 meters, and it means that this is divided by 0.03 squared. 0.03 is our value of R. So our answer here will be 50 newtons. So we find the final force that is acting on Q3 due to Q2. That's going to be Q3. Q2, divide that by 4 pi epsilon naught R. That's going to still be 9 times 10 to the power 9 times 5 times 10 times Q3, which is 5 times 10 to the power negative 6. Multiply that by Q2. Now Q2 is 3 microcoulombs, so it's going to be 3 times 10 to the power negative 6. Divide all that by their separation. The distance between Q3 and Q2, the distance is 4 centimeters. Converting that to meters is going to give you 0.04 meters, and so it means that this is going to be equal, divide that by 0.04, and this is squared. So our answer here will be 84.4 newtons. That is our force, the force acting on Q3 due to Q2. So now at the end of the day, this is what we have. We are having a charge, a point charge, but that we are calling Q3, and it is having 3 forces acting on it in this kind of manner. It is having a force acting that way, FQ2, which we have found to be 36 newtons. So from this we are going to now resolve these forces along the x-axis and along the y-axis, and then we will be able to get the resultant of the forces. So after the analysis, this is what we have. This is our point charge, Q3. It's here. And it is subject to the forces Q2, which is 84.4 newtons in that direction, Q4, 50 newtons, pulling it in this direction, and 36 newtons, pulling it in that direction. And our task here is to find the resultant force acting on that point. Finding the resultant force acting on that point means that we are going to resolve each of these forces both in the x and in the y. So we shall get the total resolution of forces in the x direction, we get the total resolution of forces in the y direction, and we get the resultant using this formula. So we begin getting the resolution of forces. So we first have to get the resultant force in the x direction, resultant force in the y direction for each force. So we shall get the resultant force for FQ1 plus the resultant force both in x and y direction for FQ2, which is that. Then the resultant in that direction also, FQ4. So we go ahead and say for FQ1, which is this force, resolving it in the x direction, it is FQ1, this force, cosine of theta. How does that come about? If you look at our diagram, we'll try to complete it like this. You find that it's inclined at an angle theta. And this point Q, remember, is at a certain point in R square, as per our question. According to our question, this is 4 centimeters, this is 5 centimeters, this is 3, that is 3 centimeters. So let's transfer this information down here. Here is 4 centimeters. Right here is 3 centimeters. So meaning this is 5 centimeters. According to Pythagoras' theorem, this is 5 centimeters, the diagonal. Now this is our angle of inclination, theta. And if you look at this theta, this angle is equivalent to that angle. Those are vertically opposite angles, so this angle is also the same as that. This theta is the same as that. So as we are resolving this FQ in the x direction, so it is FQ1, the cosine of theta, because we are resolving along that. And it is negative because it's on the negative side, so it's negative that. Resolving it in the y direction, we are resolving it along this direction. It is negative, and so it's going to be FQ, that is 36, times the sine of this angle to get the component in the y direction, which is that. Then we go ahead, this is going to be plus FQ2. FQ2 has only the component in the x direction, in the positive x direction, so it is positive 84.4. And in the y direction, this force does not have any component, so that is 0. Plus FQ4. FQ4 has got no component in the x direction, so that's how we have a 0. And then in the y direction, it is negative 50 newtons. So we do the arithmetic, we substitute for those cases here. How do we get cosine of theta? Remember, we said that this theta is the same as that theta, so to getting this cosine of this theta, cosine of theta is going to be equal to opposite over hypotenuse. Opposite of this theta is 3 over hypotenuse, which is 5, so it is going to be 3 over 5. And then the sine of that, the sine of theta is simply going to be adjacent, which is 4 over hypotenuse, which is 5. 4 over 5. And that's how we get the figures for which we substitute for this cos and this sine. So it becomes FQ1 is 36. So it's 36 times that, plus that, and this. So we'll end up with the total resolution of forces in the x direction is 55.6 newtons, and the total in the y direction is 71.6 newtons. So to find the resultant is to simply find, we substitute in the x bar squared plus the y bar squared. Our resultant force is 90.65 newtons. So if our resultant force is 90.65 newtons, it means that our point charge Q3 is like this. This is our point charge Q3. It is in the x direction, it is positive 55.6, so it is acting in that direction. 55.6 newtons. And in the y direction, it is acting in the direction, it is negative 71.6, so that's why it's pointing downwards as 71.6 newtons, because it is negative. So finding the resultant of this, the resultant lies along there. The resultant force, let's call the resultant force R. And it is inclined to the horizontal at a certain angle, we shall call alpha. So getting this resultant is what we are using. We used Pythagoras theorem to get the resultant. 55.6 squared plus 71.6 squared. Because at the end of the day, this is 71.6, the same as this. 71.6. So this squared plus that squared should give us that resultant squared. And that's how we get 90.65 newtons. So after getting the 90.65 newtons, now we seek to find the direction of the resultant force. The resultant force is inclined to the horizontal at a certain angle we have called alpha. So to get that angle alpha, we shall use trigonometry. Tan of alpha, which is that, is going to be equal to opposite. The opposite of this angle is 71.6, which is that. Divide that by adjacent. The adjacent is 55.6, which is that, 55.6. So we shall end up with our alpha as 55.2 degrees. So we shall conclude by saying that the resultant is 90.65 newtons at 55.2 degrees to the horizontal. That brings us to the end of this video. Thank you for tuning in. Please don't forget to comment below and hit that like button. Someone out there may like to watch this tutorial. Don't forget to share. Otherwise, for more videos, simply subscribe to this channel. For Kisembo Academy, this is Arnold Rwangakuremi. Electric field intensity. Call it the field strength. It's Kisembo Academy, and thanks for tuning in. Electric field intensity is simply the force acting on a charge of 1 coulomb at that point. We have explored before an electric field and what it means. It is simply the area where the electric strength is felt. So the electric field intensity is simply the force that is acting on a charge of 1 coulomb that is placed at that point. And E will stand for our electric field intensity. So electric field intensity, which we have labeled as E, is going to be equal to the force of that field, divide that by the charge of that coulomb we are talking about. So it means that the SI unit for electric field intensity is newtons, which is coming from force, and the charge Q, which is coulombs. So it is newtons per coulomb. And if we are to reorganize this into a flat equation, we find ourselves having force, electric field, the force in an electric field is equivalent to the charge, multiply that by the electric field intensity. We are deriving E is equal to intensity is equal to 1 over 4 pi epsilon naught times that. Now we are having 2 point charges here. We are having charge Q naught and we are having charge Q1. They are separated together by a certain distance. Let's call that distance R. The distance of separation between Q0 and Q1. Now, the force that is acting on Q1 due to this is going to be gotten using Coulomb's law of electrostatics, which states that for 2 point charges, the force that is between them is directly proportional to the product of those charges and inversely proportional to the square of their separation, and that is what exactly we used here, that the force F on Q1 due to Q0 F is going to be equal to 1 over 4 pi epsilon naught times Q0 times the product of the charges, divide that by the square of the separation. Like we had earlier intimated, 1 over 4 pi epsilon naught, this is a constant, and by experimental observation, it is equivalent to 9 times 10 to the power 9. But knowing that the force acting on Q1 due to Q0 is this, we are interested in finding the intensity at this point. So the intensity E at Q1 is going to be the force acting at this Q1, divide that by the charge Q1, which we have illustrated here, that the intensity due to Q1 is going to be equal to the force that is acting on that Q1, divide that by that charge Q1. And the force is what we had already illustrated here before. So we substitute for F, we put this. So it's going to be Q0 times Q1 over 4 pi epsilon naught times R squared, divide that by Q1, which is so happens to be the charge, which is that. So continuing with our arithmetic, we end up with this arrangement. We find the reciprocal of this, giving us 1 over Q1. This goes with that. You remain with our formula for intensity of a point charge E being equal to Q0, divide that by 4 pi epsilon naught times R squared. Now, let's take note of a few things. That the electric field intensity will act radially outwards for a positive charge and radially inward for a negative charge. Let's look at a works example. We have an example here. We have a point charge here and a point charge there. This is 4 microcoulombs, and we are being asked to find the intensity at B. For us to find the electric field intensity at B, which we shall call E, electric field intensity at B, from our formula we had already, it's going to be the charge, divide that by Q divided by 4 pi epsilon naught times R squared. So we are finding the electric field intensity at B due to this charge. So the value of Q here is the value of the charge which is having the electric field intensity, which is causing the field intensity. So in this case, our value of Q is going to be 4 times 10 to the power negative 6, because it is microcoulombs. Divide that by R squared. What is R squared? It is 5. Converting this to meters is going to give you 0.05 squared. And this multiply that by, we have 4 pi epsilon naught. 1 over 4 pi epsilon naught is equivalent to 9 times 10 to the power 9. And to get our answer there will be 14.4. And that is newtons per coulomb. So that's the electric field intensity at B due to that point charge. 14.4 times 10 to the power negative 6. Let's find the intensity at point B. In this question, we are having point A with a point charge of positive 5 microcoulombs and negative 3 microcoulombs. So if we are to redraw that diagram, this is what we have. We have B, we have C here, we have A. Now we know that A here is positively charged, C is negatively charged. So we shall assume that B is positively charged. Now if this point B is positively charged, it means that there's going to be repulsion between A and B. And it means that the intensity at B due to A is going to be experienced in that direction. Considering that this is stationary, that is stationary, and this is the only one that is moving, it means that our intensity due to A will be experienced in that direction. Likewise, if we look at point C, it is negatively charged according to our question, negative 3, and this B is positive. Since this is positive and that is negative, it means these are unlike charges, so they will attract. So it means that the intensity of B due to C is going to act in that direction still, assuming that C is stationary and B is the one that is moving. It means it is going to be attracted in that direction. So it means that our intensity, electric field intensity due to C, is also going to be acting in that direction. So we begin off we find the intensity in that direction, we find the intensity due to C. Then since both of them are acting in the same direction, it means we shall simply add the two and we have an answer. Intensity due to A, using the formula, is going to be QA over 4 pi epsilon naught R squared. Intensity, electric field intensity due to A is going to be, QA is 5 microcoulombs, so it's going to be 5 times 10 to the power negative 6 times 9 times 10 to the power 9. Remember, this is equivalent to 1 over 4 pi epsilon naught. Divide that by R squared. This is 10 centimeters. Converting that to meters is going to give us 0.1 meters, so it's going to be 0.1 squared. And our answer will be 4.5 times 10 to the power 6 newtons per coulomb. We go on to the next. The intensity due to C. This is simply going to be QC over 4 pi epsilon naught R squared. That's going to be, our QC is 3. It is 3 microcoulombs, so it's going to be 3 times 10 to the power negative 6. Multiply that by 9 times 10 to the power 9. Divide all that by this distance between the two is 5 centimeters. In meters, that is 0.05 meters. So it's going to be 0.05 meters squared. And our answer here is simply going to be 10.8 times 10 to the power 6 newtons per coulomb. So since the intensity due to A is acting in the same direction as the intensity due to C, so to find the total intensity at point B is simply, you are going to add the intensity due to A and intensity due to C, and we'll get the total intensity. So in this case, it will be, so our total intensity will be, intensity at B is going to give us the intensity due to A plus the intensity due to C, and that is going to give us 4.5 times 10 to the power 6, because that is what we got here, plus 10.8 times 10 to the power 6, and our answer will be 15.3 times 10 to the power 6 newtons per coulomb. And that is going to be the intensity at point B. Please don't forget to comment below or hit that like button. Someone out there might like to watch this tutorial. Don't forget to share. Otherwise, for more videos, simply subscribe to this channel. For Kisembo Academy, this is Arnold Rangakura. Electric flux, according to electromagnetism, refers to the measure of flow of the electric field through a given area. It is directly proportional to the number of electric field lines that are going through a perpendicular surface. Today, we get to discuss more about electric flux. It's Kisembo Academy, and thanks for tuning in. Now, looking at the illustration on your screen, we are having a surface. This surface, the area of this surface, we've labeled that A, and we are having some lines that are going through this surface, and these lines are what we are calling the electric field lines. And like I had earlier said, flux is simply going to be the flow of these electric field lines through this surface area A. Now, if you want to calculate the electric flux that is going through this surface, flux is denoted by that, which is that flux is going to be equal to the E times A. E is simply the electric field intensity of the field lines that are going through the area, and A is the area or the surface area, and that's the formula. So meaning that flux through an area A, which we have showed here, that is perpendicular to the lines of force, is going to be equal to E times A. So here the condition is that the field lines should be perpendicular to the lines of force. In this case, they should be 90 degrees to the surface through which they are going through. So now what if these lines are going through this area at an angle that is not 90 degrees? If they are going through the surface at an angle theta, it means that if we are trying to find the flux of these lines that are going through the surface, it means that we're going to have to resolve these field lines to the normal. If the field intensity makes an angle theta with the normal to the plane, then the electric field flux is going to be resolved to the normal. Like we are seeing here, it's going to be E cos theta times A. The cosine of theta is the resolution of these field lines to the normal. So it's going to be E cos theta times the area. It's more or less like previous. Let's look at this diagram here. We are having this spherical ball. It is a sphere with radius. It's having a point charge in the middle, in its center, and this charge is radiating out field lines. The field lines are coming from the center of this spherical ball. So now if we are to consider a spherical surface and we want to find the total flux that is going through this spherical surface, remember these field lines, as they are getting out from the point, from the center of the sphere, they are going to collide with the sphere's surface, the spherical surface, at 90 degrees. So it means that for us to find the flux that is going through the spherical surface, it will be the electric field intensity of that point source. We multiply that by the area through which they are going, and in this case the area is going to be the total surface area of this sphere, and that is what is explained in our next write-up. The total flux is through the spherical surface that is going to be this times that, the intensity times the area. So the electric field intensity times the surface area of a sphere, which is 4 pi r squared, and it's going to be equal to, the intensity is is q over 4 pi epsilon naught r squared, multiply that by 4 pi r squared, which is that, and when these common terms disappear, 4 pi disappears with 4 pi, r squared disappears with r squared, you remain with epsilon naught here, q over epsilon naught, and so you find that flux is going to be q over epsilon naught. Q is the charge that is inside the sphere, and epsilon naught is simply the permittivity of free space. And now this relation that we are seeing is what is going to constitute what we'll call Gauss' law of electrostatics. So what is Gauss' theorem, or the Gauss' law of electrostatics? This theorem states that the total flux passing normally through any enclosed surface, whatever its shape, is always equal to q over epsilon. If you want more videos, simply subscribe to this channel, and for the benefit of your colleagues out there that would like to watch this tutorial, simply share this video. Otherwise, thanks for watching and hope to catch you in the next video. For Kisembo Academy, this is Arnold Ranga Kuramia. An electric charge creates an electric field in the space around it. It also creates a related quantity we shall call an electric potential. This tutorial seeks to explain the concept of the electric potential. It's Kisembo Academy, and thank you for tuning in. Today, we are going to describe what we exactly mean when we say electric potential. In this diagram, we have a test charge. We have a charge Q, which is positively charged. We are also having a test charge. This is in its initial position here. This is a charge Q. Now, initially, this charge was here. This is the initial position of our test charge, which is positively charged. And this charge is within the electric field of this charge, the big one. So this charge Q was moved from this point to that point. Now, if this charge is positively charged, and this charge Q is also positively charged, it means that bringing these two charges, it means will be repelling each other. This will be repelling this charge, because this is positive and that is positive. Meaning, for us to be able to move this test charge from this point to that point, it would mean that we will have to do work against this charge, because we are working against the repulsive forces of these charges. So it means that work has to be done for us to move this test charge from here to there, because these two are the same charge because of the repulsive forces. So in this case, if work done in moving this test charge we're talking about, which is this. If work done in moving this test charge Q from infinity to some point P near Q is W, then it means that the potential of point Q is given by work done per unit charge. For us to get the potential of this thing at that point, it's going to be that work done per unit charge, which is the potential V. And the SI unit for potential is coming from the formula work done per unit charge. Work is in joules and Q is in coulombs. So it means that the SI unit is going to be joules per coulomb, which is equivalent to 1 volt. So to describe what exactly electric potential is from that background, we shall say that the electric potential at a point in an electric field is simply defined as numerically the work done in bringing a positive charge of 1 coulomb from infinity to that point, and the unit is the volt. So let's look at the electric potential due to a point charge. Here we are having charge at x naught, x naught, charge at A, we have charge at x1 at B, and these two, A and B, are separated by distance x, and of course the force is in that direction because they are repelling each other. Now the point charge at A, which is this one, which is Q, is exerting a repulsive force on charge B, that is charge B, and that is why that arrow is pointing in that direction, because they are both positive. This charge B is being repelled in that direction, in the opposite direction. So meaning the repulsive force that exists between this charge and that charge is going to be equal to, the repulsive force is going to be directly proportional to the product of those two charges and inversely proportional to the square of their separation, which is x. So the repulsive force is going to be equal to that. And so we are going to use this to derive the formula for electric potential due to a point charge. If the charge at B is going to be moved towards A by a very small distance, we shall call dx, a very small distance, it means that the work done, the small change in work done, is going to be force times the small change in distance. If charge at B is moved by some external agent by a small distance, we are going to call dx, towards A, where that small distance it has been moved is so small, if considered constant, then the work done by the external agent will be given by that. The change in work, the work is going to be, you know that work is equal to force times distance. So the work is going to be equal to force times distance. Now, if you have to look at these 2 point charges, this is positive and that is positive. So this charge is exerting a repulsive force. So it is pushing this thing away. But our external agent is pushing this charge in the opposite direction to the repulsive force. That is why we are having a minus sign here. It simply signifies that. So meaning the work done is going to be equal to, we substitute for the value of F, so our force is going to be from Coulomb's law, which is Q naught times Q1 over 4 pi epsilon naught x squared times the small element in the distance moved towards the charge. So it means for us to find the work done from 0 to the actual work is going to be, we are going to integrate on both sides. It's going to be equal to work done in moving that charge from infinity to a point R. So it means we are going to integrate this expression with respect to x. So integrating this side will leave us with work is going to be equal to, now if you look at this expression, Q naught times Q1, this is the charge of the charge at A, this is the charge at B. These are both constant terms. 4 pi epsilon naught, all these are constant, so we shall put them outside the integral sign, and we shall only integrate x squared, 1 over x squared with respect to x. So when we integrate, this 1 over x squared is the same as x to the power negative 2. We are integrating with respect to that. So from our rules of integration, integrating this is going to be, we add 1 to the power and divide through by the new power, which is negative 2 plus 1. And this is running from infinity to that point R. So we'll end up with negative negative 2 plus 1 is negative 1, and then negative 2 plus 1 down here is negative 1, so we shall end up with negative x to the power negative 1. So now we substitute in for r here. This negative x to the power negative 1 is the same as negative 1 over x. We substitute in our limits of integration. It's going to be 1 over r, we get that from here, minus, we substitute for infinity there, negative 1 over infinity. So from here we'll end up with this expression, we'll end up with negative 1 over r. So this negative and that negative, multiplying these two will give us a positive. So we shall end up with our expression for work as work is going to be equal to q naught q1 over 4 pi epsilon naught times r. In this regard, therefore, the definition of potential V at a distance r from a point charge q in a medium of permittivity epsilon naught is given by that. We have got our expression for work, which is q naught times q1 over 4 pi epsilon naught, from our derivation, and we are asking ourselves that now from this, how do we come to that? Our V is going to be, it's our potential, remember from our previous explanation was, it is going to be the work per unit charge. And in this case, we are looking at charge Q1. So it's going to be work, divide that by Q1. But what is work? Work is what we had. This is what we've gotten here. So work is Q naught times Q1 over 4 pi epsilon naught, divide that by Q1, which is the Q1 we have there. So it means that this Q1 and that Q1 are simply going to cancel out. And then we shall remain with our expression. V is going to be Q naught over 4 pi epsilon naught times r. This is our expression for the point charge, of the potential of a point charge in a field, and that is how we come to this. And that is how we conclude by saying that therefore the definition of potential V at a distance r from a point charge q is a measure in a medium of permittivity epsilon naught is given by that expression. I would encourage you to subscribe to this channel if you want more of these videos, and for the benefit of your colleagues out there that would like to watch this tutorial, simply share this video. Otherwise, thank you for watching and hope to catch you in the next video. For Kisembo Academy, this is Arnold Rangakurami. In our previous video, we had just derived V is equal to Q over 4 pi epsilon naught. We explained how it comes about. Today we get to look at a few worked example where we will require to use this. This is Kisembo Academy, and thanks for tuning in. We'll start it off with the first example. We have a point charge, 10 microcoulombs. It is 10 centimeters apart from a point R, and they're asking us to find the potential at point R. So for us to find the potential at point R, we know that V, the potential V, is going to be equal to Q over 4 pi epsilon naught times their separation, which is R. That is going to be equal to, our value of Q is 10 microcoulombs, so it's going to be 10 times, micro means 10 to the power negative 6, then coulombs. So it's 10 times 10 to the power negative 6 coulombs, divide that by 4 pi epsilon naught times R times the separation. The separation is 10 centimeters, but this separation has to be in meters. So we convert that to meters, and that is going to give us 0.1 meters. So this is going to become, now remember that 1 over 4 pi epsilon naught from experimental observation is equal to 9 times 10 to the power 9, because this is a constant. So it means that this is going to be 10 times 10 to the power negative 6 coulombs. Multiply that by that constant, which is 9 times 10 to the power 9. Divide all that by 0.1. And so our answer is going to be 9 times 10 to the power 5 volts, and that will be our answer. Let's get to the next example. In our next example, they're asking us to find more or less the same thing, only that here our charge is negative. So find the potential at X. Same story. V is going to be that charge Q over 4 pi epsilon naught times the separation, we shall call R. So that is going to be equal to, if we are finding the potential at X, it means the Q, our value of Q is going to be the charge here, which is negative 5, times 10 to the power negative 6 coulombs. Multiply that by the constant, which is 9 times 10 to the power 9. That is 1 over 4 pi epsilon naught. Divide that by r. Our separation is 20 centimeters. Converting that to meters is going to give us 0.2. And our answer there will be negative 225 times 10 to the power 3 volts. Let's look at one more example. In this example, we are having 2-point charges. We are having negative 5 microcoulombs, and we are also having 10 microcoulombs, and they are asking us to find the charge, the potential at B. So it means you are going to first find the potential at B due to A. We find the potential at B due to C. Then afterwards, we shall find the total potential that is acting on point B. So we will begin. So potential at B due to A, we'll call it VA, is going to be, we'll still use our formula Q over 4 pi epsilon naught times R, and that's going to be, our Q is negative 5 times 10 to the power negative 6. Multiply that by, this is 1 over 4 pi epsilon naught, which is 9 times 10 to the power 9. Divide all that by R, that is 0.1 meters. If you convert the distance of separation here, it is 0.1. So that is going to give us an answer that we've already gotten before, which is negative 4.5 times 10 to the power 5 volts. So let's find the potential at C due to B. So VC is going to be Q over 4 pi epsilon naught times R. That is going to be Q, which is 10 microcoulombs. So it is 10 times 10 to the power negative 6 coulombs. Multiply that by the constant, which is 1 over 4 pi epsilon naught, which is equivalent to 9 times 10 to the power 9. Divide all that by the separation. The separation here is 5 centimeters. Converting that to meters is going to give us 0.05 meters. And the answer we shall get here will be 1.8 times 10 to the power 6 volts. So now for us to find the total potential at B, it means that we are going to add the potential at B due to A, which is negative 4.5 times 10 to the power 5. And we also add the potential at B due to C, which is 1.8 times 10 to the power 6. And then we shall get our total potential. So we go. So meaning that the potential at B, V, is going to be potential due to A plus potential due to C. And that is simply going to be equal to negative 4.5 and our answer here will be 1.35 times 10 to the power 6 volts. And that will give us the potential at B. If you want more of these videos, simply subscribe to this channel, and for the benefit of your colleagues out there that would like to watch this tutorial, simply share this video. Otherwise, thanks for watching and hope to catch you in the next video. For Kisembo Academy, this is Arnold Rangakuramia. In our previous tutorial, we introduced the electric potential. Now we are going to discuss about electric potential difference. Consider this tutorial a continuation of the previous one. It's Kisembo Academy, and thanks for tuning in. If this point has a lower potential and this has a higher potential, so the work done in moving this potential, this charge from a position of low potential to a position of high potential is what we are calling potential difference. In this tutorial, we shall derive the formula of work done in moving this charge from this point to that point. We all know that potential, the unit of the potential is called the volt, and which volt is equivalent to 1 joule per coulomb. So what is the volt? By definition, the volt is simply the potential difference between 2 points when the work done in transferring 1 coulomb of electric charge between the 2 points is 1 joule. And like earlier said, 1 volt is equivalent to 1 joule per coulomb. So let's go ahead and derive the electric potential formula. the potential difference formula. Here we are going to consider a charge Q, and we have also two other test charges. Now these charges A and B are lying on a line of force. The line of force is due to this charge Q. Supposing A and B lie on a line of force at a distance A and B separately from charge Q, we are having A lying at a distance A. We are also having B at a distance B. These are points along this line of force, lying on that line. Now when a unit charge is at a distance x from Q, this is the unit charge we are talking about. It is at a distance x from Q. While in free space, then the force acting on it. So now the force acting on this unit charge is we are going to get this force from Coulombs law of electrostatics, which is going to be 1 over 4 pi epsilon naught times Q, the product of the two charges Q. The Q we are talking about is this charge Q, times this unit charge positive 1. So it is Q times 1 over x squared. So meaning that this unit charge can either move from B to A or from A to B. Now, if this unit charge is to move from B to A, it would mean that it's going to work against the repulsive forces of this Q, because this Q is also positively charged. So it means that work is going to be done against the forces of the repulsive forces of Q. And if this unit charge is to move from A to B, it means that this Q, this charge is going to do work in pushing it away. So now what I'm trying to say here is that the work that is done against the repulsive forces in bringing B to A is going to be the same as the work done by these repulsive forces in pushing A to B. So we continue with our write-up. Work done on taking the charge from B to A against F, or against the repulsive forces of the charge Q, is equal to the work done or work which force F will do if the charge were allowed to go from A to B. The force F we are talking about is the force due to the charge Q, the force which we have gotten here as 1 over 4 pi epsilon naught times that. Now, over a short distance dx, the work done by the force F is given by the small change in work is equal to force times that small change in distance. That small change we are talking about is this. If this thing is to move, this test charge is to move from, let's say, that point to that point, and it is to go through a very small distance dx. So it means that the work done in moving from that, to move through that small distance, is going to be the force times that small change in distance. And that is what this expression means here. Now, what if we wanted to find the work done for that force to move the entire distance? By the entire distance, we are talking about if this test charge is to move from A to B, a significantly very big difference. So meaning that over the whole distance AB, work done by the force on the unit charge, that is work done to move from A to B, is going to be equal to force times distance. So it means you are going to integrate from the point when x is equal to A to the point when x is equal to B. And these distances are the distances from the charge Q, capital Q. So integrating that would give us, we substitute for the value of F, and so it means that work is going to be equal to Q over 4 pi epsilon naught, which is the F we have substituted, multiply that by 1 over x squared. This is Coulombs law, we've just substituted for F, dx. And it's running from A to B. Now if you realize Q over 4 pi epsilon naught, this is a constant, so we'll put it outside the integral sign, and inside will remain with 1 over x squared. So 1 over x squared is what we shall integrate. 1 over x squared is the same as x to the power negative 2. So x to the power negative 2, integrating x to the power negative 4 running from A to B is going to be equal to x to the power negative 2. We add 1, to the power, and the answer we get here we divide by the whole term, like illustrated here. And so negative 1 plus negative 2 plus 1, here we get negative 1. Negative 2 plus 1, we shall get 1. Negative 1. And that's the negative that is going outside here. And so when we are to substitute in our expression here, we are going to end up with negative q over 4 pi epsilon naught times 1 over x. X to the power negative 1 is the same as 1 over x. It's running from b to a. Substituting b in this expression is going to be 1 over b, minus substituting a in that expression is going to be minus 1 over a. That's the expression we have. So multiplying this negative through these brackets, it would mean negative this times 1 over b and negative this times that. It would mean that this is going to become positive 1 over a. So that's how this comes to this. We have this as positive, which is equal to 1 over a minus 1 over b. And that will be our expression for the work done. If you want to watch more of these videos, simply subscribe to this channel, and for the benefit of your colleagues out there who would like to watch this tutorial, simply share this video. So this is our expression for work done. Work is going to be q over 4 pi epsilon naught into 1 over a minus 1 over b. But we are interested in finding the potential, not the work done. So how do we get the potential? Remember, in our definition of potential, when we were introducing potential, we said that that potential V is equivalent to the work done per unit charge. We said that potential is going to be work done per unit charge. And remember that this being our work done, when we were deriving this, we were considering a charge Q and another test charge which we called positive 1 coulombs from our diagram. It was Q and the other charge was positive 1 coulombs. So it means that for us to get our value, the potential difference formula, we get it by the work done per unit charge, and the unit charge we are talking about here is that test charge Q, which is positive 1. So it's going to be, we substitute for the expression for the work done, the expression that we just got earlier, which is Q times that positive 1 coulomb of charge, divide that by 4 pi epsilon naught times 1 over a minus 1 over b, which is just, this is the substitution for the work done, divide that by the test charge Q, which is positive 1, which is that. So our expression is that, which is this, divide that by 1. And so our potential will end up being Q over 4 pi epsilon naught into 1 over a minus 1 over b. So this is the expression for potential, for the potential difference between 2 points. And our value of a is the distance between Q and A. A is the smaller distance and B is the longer distance. So it means that A, which is the shorter distance, should come first, and then B, which is the longer distance, should come later. Thank you for watching. I would encourage you to subscribe if you want to watch more of these videos. Otherwise, for the benefit of your colleagues that would like to watch this tutorial, simply share the video. For Kisembo Academy, this is Arnold Ranga Kuramia. In our previous tutorial, we derived the potential difference formula. Consider this a continuation of that as we explore a few worked examples where we will be required to use that formula. We have a question here, 2-point charges, 15 microcoulombs and 7 microcoulombs. We have 15 microcoulombs here and the 7 microcoulombs. Respectively, these are 6 centimeters apart. Find the work done in bringing them 2 centimeters apart. So these two are initially 6 centimeters apart, and now we want to find how much work we will need to do to bring them 2 centimeters apart. So now, for us to find the work done, we need to assume that one of them is stationary. Either assume that the 7 microcoulomb is stationary or 15 is what is stationary. But in this case, let us assume that the 15 microcoulomb charge is stationary, and this is the one that is moving, so that the two are eventually 2 centimeters apart. So what are we going to do here? Remember, we said that work done is going to be equal to QV. That is work done. So it means that we're going to have to first find the potential difference. After finding the potential difference, then we shall simply multiply, then we get the work done. So we begin with our explanation. So we first find the potential V, and from our previous tutorial we derived the expression for potential difference. V is going to be equal to 1 over 4 pi epsilon naught, multiply that by 1 over A minus 1 over B. And we said that A is the shorter distance, B is the longer distance. So what is our value of A in this case? If this thing has moved to 2 centimeters apart, what's the potential difference? So if we are assuming that 15 microcoulombs is the one that is stationary, it means that our value of A is going to be 2 centimeters, which is 0.02 meters, and our value of B is the longer distance where this thing has come from to move from here to here, which is 0.06 meters. So we simply substitute. So if this is the stationary one, it means that it's going to be Q over 4 pi epsilon naught into 1 over A minus 1 over B. So what is our value of Q in this case? Our value of Q is the stationary point, which is 15 microcoulombs. So it's going to be 15 microcoulombs, which is going to be 15 times 10 to the power negative 6 over 4 pi epsilon naught into 1 over 0.02 minus 1 over 0.06. So we shall end up with, now this is going to be equal to 15 times 10 to the power negative 6, multiply that by 9 times 10 to the power 9 into that, and our answer here will be 4.5 times 10 to the power 6 volts. So we continue with getting the potential. So V is going to be Q over 4 pi epsilon naught into 1 over A minus 1 over B. This is the expression for potential difference that we derived in our previous tutorial. Our value of Q in this regard is the stationary point we have chosen, which is 15 microcoulombs. So substituting here is going to be 15 microcoulombs into 1 over 0.02 minus 1 over 0.06. 0.02 is our value of A, which is happens to be the shorter distance, and 0.06 is our value of B, which is the longer distance. And we said that 1 over 4 pi epsilon naught is 9 times 10 to the power 9 according to experimental observations. So it means that 15 times 10 to the power negative 6 over times 9 times 10 to the power 9 into whatever we have here in the brackets is going to give us 4.5 times 10 to the power negative 6. This is the potential difference V that we have gotten. So after getting our potential difference V now, we need to find the work done. The work done in moving this charge from here to 2 centimeters apart, because that is what the question requires. So to get the work done, we know that work done is going to give us Q times V. What is our value of Q? The work done in moving a charge of 7 microcoulombs from this point to that point, so that these two charges are 2 centimeters apart, is going to be the Q, which is the charge in question, the charge that is moving. So it is going to be equal to 7 microcoulombs, which is 7 times 10 to the power negative 6 coulombs. Multiply that by the potential difference, which is 4.5 times 10 to the power 6. And our value of work is going to be 31.5 joules. 31.5 joules, and that is the work done in moving that 7 microcoulomb from 6 centimeters to 2 centimeters. And that brings us to the end of our worked example. I would like to encourage you to subscribe to this channel if you want more videos, and for the benefit of your colleagues out there that would like to watch this tutorial, simply share the video. Otherwise, thanks for watching and hope to catch you in the next tutorial. For Kisembo Academy, this is Arnold Rwanga Kuramya. In this tutorial, we shall discuss the relationship between electric field intensity and electric potential. It's Kisembo Academy, and thanks for tuning in. Let's consider a charge Q. If a charge Q has been moved from point A to point B within an electric field with an intensity E, it would mean that there is a potential difference between A to B, and there is some work that has been done in moving that charge from point A to B. Now, supposing this charge has been moved through a small distance, let's call that distance dx. It means that the work done in moving that charge from A to B through that small distance is going to be equal to force times that small change in distance. Now, for us to substitute for the value of F, the force, it will follow. We'll get it from the formula for intensity. Remember, we said that intensity is the force per unit charge in the field. So it follows that from the definition of electric field intensity, intensity E is the force per unit charge. And so if we are to make F the subject of the formula, it would mean that F is going to be E times Q. And we said that that negative is going to be as a result, because the charge that is being moved, it is working against the repulsive forces, the other 2 point charges. So it means that we substitute this value of F in that point. And so it means that our new value of work, hence the work is going to be E times Q, which is that, times the small change in distance. And that will be our first relation, or our first equation. So now we have another expression for work, which is work is Q times V. If the potential difference between A and B is dV, where B is at a higher potential than A, then in terms of potential difference, it means that work done is going to be the charge times the change in potential difference, and that is going to be our second expression. So what we do, we equate these two expressions. Work done here is equal to that. The work done in terms of potential difference is that. So it means that it is this expression is equal to that expression, and that is what has been done down here. The work is going to be equal to the work. So the expression, the first expression, equation 1, is going to be equal to the second expression. And if you divide both sides here by Q times dx, Q and dx, this dies with that, and then this goes with that. You remain with our intensity as being equal to change in V over change in X, change in potential difference over change in the distance. So this is the relationship that exists between electric field intensity and potential difference. So to note, NB, dV dx is the rate of change of PD with the distance in the electric field, which is also the potential gradient at that point. So where does this leave us? It gives us an expression that in uniform fields, therefore, intensity is going to be equal to the potential difference with the potential difference, divide that by the distance. This brings us to the end of this video. Simply subscribe to this channel for more, and for the benefit of your colleagues that would like to watch this tutorial, simply share this video. Otherwise, I'll catch you in our next video. For Kisembo Academy, this is Arnold Ranga Kuramia. We have two large horizontal plates that the upper plate is positively charged and the lower plate is negatively charged. From the relationship between electric field intensity and electric potential, we were able to discover a relationship that if we are to find the electric field intensity in between these two plates, that electric field intensity would be equal to the potential difference between that field and the distance in between. And when we are looking at two plates like this, it is as simple as this is a uniform field, and looking at this uniform field, we know that the intensity that exists between this uniform field is going to be the potential difference between these two plates. Divide that by the plate separation, and this plate separation in this case has been denoted by D. We shall look at a worked example. We have two horizontal plates. These two horizontal plates are 2 centimeters apart as shown in the diagram. Two horizontal plates are 2 centimeters apart and they are in a vacuum, and the upper is maintained at a positive potential relative to the lower plate. Now, the upper is maintained at a positive potential relative to the lower plate, so that the field strength between them is 2.5 times 10 to the power 5 volts per meter. So it means that our value of E here is going to be 2.5 times 10 to the power 5 volts per meter. That is the meaning of that. So they're asking us to find the potential difference between the plates. So what is the PD between these plates? The potential difference between the plates, we know that our intensity E is going to be potential difference V over D. So meaning that to find our potential difference V is going to be equal to E times D. What is our intensity? Our intensity is 2.5 times 10 to the power 5. So that's going to be 2.5 times 10 to the power 5. Multiply that by the plate separation, which is 2 centimeters. Our plate separation being 2 centimeters, we convert that to meters. And so it's going to be 0.02 meters. So it's going to be 0.02 meters. And our potential difference between the plates is simply going to be 5.0 times 10 to the power 3 volts. If an electron charge of 1.6 times 10 to the power negative 19 and mass of 9.1 times 10 to the power negative 31 kilograms is liberated from rest at the lower plate, find the speed of the electron on reaching the upper plate. These are our two plates. We are having an electron here, and it is being liberated towards the positive plate, and they are asking us to find the speed by which it is liberated from rest, from this lower plate to the upper plate. So let's get one thing here, that when this electron here, it is having a charge, it is an electron, meaning that it is negatively charged. If it is negatively charged, it is definitely going to be repelled from this negative plate, and it is going to be pushed towards the positive charge as a result. So while it is moving up, at first it has electric potential energy. So as it is moving up, this electric potential energy, while it is in this field, is being converted into the kinetic energy with which it is going to use to move to the upper plate. So it means that from the law of conservation of energy, we know that energy can neither be created nor destroyed, but can be changed from one form to another. So it means that the electric potential energy that was possessed by this electron while it was in the field has been converted into the potential energy with which it is moving towards the plate. And so that is our first step, that the electric potential energy has been converted, or it is going to be equal to the kinetic energy of the electron. And the electric potential energy here is, which is actually the work done, is QV is equal to the kinetic energy with which the electron moves, and that is going to be a half times the mass of the electron times the velocity with which it moves, V squared. So making U the subject of the formula, because we're interested in finding the velocity with which it moves, U is going to be equal to the square root of 2 times the charge times the potential difference between the plates, divide that by the mass. So it's going to be 2 times the charge on the electron, which is 1.6 times 10 to the power negative 19, times the potential difference, which is going to be 5.0 times 10 to the power 3. We got this potential difference in our previous, because it's a continuation of this. It's 5.0 times 10 to the power 3 volts. Divide that by the mass. The mass of the electron is a constant that was even given in the question, which is 9.11 times 10 to the power negative 31. And we end up with our answer as 4.2 times 10 to the power 7 meters per second. And that is the velocity with which it moves. This brings us to the end of this video. Thank you for watching. I encourage you to subscribe if you want more of these tutorials. Otherwise, for the benefit of your colleagues out there who would like to watch this tutorial, simply share this video. Thanks for watching and hope to catch you in the next tutorial for Kisembo Academy. This is Arnold Rangakuramia. So in today's session, I get to explain one of the applications of electrostatics, and one of them is electrostatic paint spraying. Now, it's a very simple concept. Right here, what we are seeing is just a simple diagram with what we may call a spray gun. So in other words, the person that is going to spray is going to handle this like he's handling a gun, and as they are spraying, these dotted lines you're seeing are simply our spray particles or the paint, and this is the object that is being sprayed with paint. So now what happens is that right here at the outlet of this spray gun is what we call an atomizer. In other words, what it does is that as the paint comes through here, it makes sure that as it's moving out, it is atomized. So as this paint is atomized as it moves out of the spray gun, it is charged by friction. So it is charged, and as it is charged, let's say it is charged positively as it is moving out of this spray gun, the object that is being painted is connected to the opposite charge. In this case here, we connect this to a negative electrode. So if this object that is being sprayed is connected to the negative, or it is earthed, and this is positively charged, what happens is that these particles, as they come out being positively charged, they are attracted to the object. And in so doing, you will find that even as you're spraying, if there is any paint that is even going astray, it is attracted to this object because this object is negatively charged. And we know that one of the laws of electrostatics is that, unlike charges will attract. This kind of setup ensures that there is minimal wastage of paint as the spraying is going on. So to sum this all up, that is for those that are doing their exams and you have been asked to describe how electrostatic spraying works, you can simply say that as the spray goes through the atomizer, the droplets get charged by friction. And of course, the similar charges on the droplets, because these ones are positively charged, because they are similar charges, there will be repulsion in here, and this repulsion will make, the particles to spread out. So as these particles are spread out, the surface that is being sprayed, which is this one right here, is connected to an electrode of positive charge, or we can say this surface is earthed. That is, if whatever is coming out here is positively charged, it means that this one will be earthed so that it is negatively charged, or we shall just say it is connected to an electrode of opposite charge. The paint droplets will get attracted to the surface and they will be able to reach remote areas. Now, this is not only used in paint, but even when let's say there is need to spray, maybe, these cleaning services, and you need to spray a certain surface during cleaning, maybe you're spraying it with detergent, the same application can still be used. So that's it. That is how electrostatics is applied in paint spraying. Now, in this session, I am going to explain how electrostatics is used in dust extraction. Let's assume that this is a chimney right here. This is a chimney right there, but inside this chimney there is a mesh. This mesh you're seeing here is connected to a negative potential, and these electrodes here it is more like a foil, but round like this. It is connected to a positive electrode. So in other words, this mesh is negatively charged and this is positively charged, these two, and right here are pans. So what happens is that we have smoke coming in here. So as this smoke comes in, it goes through these wire meshes, and as these smoke particles come out here, they are negatively charged as they move up. So as they gain that negative charge, as they move up, they come in here. Remember, these electrodes right here are positively charged, so these negatively charged particles are attracted to the sides, so they go and they stick to this positive electrode. The negatively charged particles will go and stick to these positive electrodes, and so as a result you'll find that this smoke that came in here with all the particles and whatever, because these particles have been deflected by this electrode, you'll end up having clean air moving out of this chimney at the end of the day. So this kind of this extractor, it's extracting dust from this, dirty air is moving in here. By the time it is coming out of there, it is clean air. So that is another application of electrostatics. And of course, the particles or the soot that has gotten stuck onto here is later shaken off and it is dropped into these pans. So for those that might want a write-up for examination purposes, you can simply say that the smoke right here is made to pass through a wire mesh, as you can see, and the wire mesh A is made negatively charged by connecting it to a negative potential. So as this smoke passes through this mesh, it is negatively charged, and definitely another electrode up here, you can call it any letter, or electrode B. This is electrode A, electrode B. You can call it electrode B and say another electrode B is placed higher up the chimney and made positive. The smoke particles are attracted to this electrode, and so when the smoke particles are attracted to that electrode, they make the gas that is going through less smoky. And of course, you can mention that the soot that gets attached here is shaken off later on and dropped into the pans. Now, this method of making sure that, dusty air is made clean is what is also used in a more advanced setup. The idea behind an electrostatic precipitator is that as flue gases enter into, this setup, they'll use the same principles like I have explained here, and at the end of the day, the gases get out when they are cleaner. In a way, this is in factories that, emit a lot of dusty particles. In order to protect the environment from pollution, they use what we call an electrostatic precipitator, which works using the same principle, and it ensures that the particles that are getting out are clean, and that protects the environment from air pollution. And that's how electrostatics applies in dust extraction.
When you place the document you want to photocopy upside down and press the start button, an intense beam of light scans across the document, as you can see in the video. This light is then reflected and it is cast onto a photosensitive drum. The makeup of the photosensitive drum is that this drum is a metal roller that is electrostatically charged by a high voltage wire called the corona wire. On top of the drum lies a photosensitive chemical, a semiconductor called cilium. A semiconductor is simply a material whose conductivity value falls between the value of a conductor and an insulator. In other words, it is not fully a conductor and it is not fully an insulator, hence a semiconductor. So this photosensitive cilium coating on the drum is photosensitive, like I've said. By this I mean that when it receives light, it is only the areas that have received light that will conduct electricity, while the areas that have not received light will not conduct electricity. In short, cilium will act as an insulator in areas that are dark or areas where light has not been reflected, and it will act as a conductor in areas where it has received light or in areas where light has been reflected onto it. Now let's assume that this is the document we want to photocopy. When the light beam from the halogen lamp scanned the paper, the light got reflected onto the photosensitive drum. Here is how the reflection happened. During the reflection, the white area of the paper reflected the light onto the photosensitive drum, whereas the black areas did not reflect the light. I assume you are well conversant with the principle that white surfaces reflect light, whereas black surfaces absorb all light and reflect none. So the reflected light onto the photosensitive drum causes the area where it has fallen to become conductive, and as a result become discharged, whereas the area where the light did not fall do not become conductive, and so the electrons in these areas remain intact. This creates an electrical shadow of the page on the photosensitive drum. So this electrical shadow is carried by the photosensitive drum towards the toner. The toner is positively charged, so since unlike charges attract, the positively charged toner particles stick into the negatively charged electrical shadow. This now creates an image of the original document onto the drum. A blank paper from the tray then moves up the conveyor, and while it moves, it is given a strong electrical charge. As this blank paper approaches the photosensitive drum, the toner remains are transferred from the drum onto the paper. The paper then passes through two hot rollers to ensure that the toner remains are fused onto the paper. This happens with the help of the heat and pressure between the rollers. So after passing through these rollers, we have a final copy of the original document. Here is Brian, a National Forensic Academy instructor, showing us how electrostatics is applied in dust lifting for evidence collection. So as you can see, a dust impression of the footprint has been located on the surface. Our goal is to remove that dust impression. So once the location of the dust impression of the footprint is known, a special film is laid over the impression. A ground plate is then installed a few inches away from the special film. We then put a charge box on top of both the special film and the ground plate. The bottom of the charge box has 3 contacts. One of the contacts lays on the special film and the other 2 contacts lay on top of the ground plate. This charge box acts as our DC source, and its role is to charge the special film. We then switch on the charge box and we see the edges of the film drawn down on the surface. After all this is done, we then turn the charge box off, remove the charge box and ground plate, and voila! We have lifted the footprint impression of the ground. The charge on the film attracts the dust with the footprint patterns, causing them to stick to it. So from that you're able to see that we are able to apply the principles of electrostatics to lift that footprint onto that special film, and this is used in special investigations in trying to determine questions surrounding crime scenes.
Charged conductors and equipotential surfaces. It's Kisembo Academy and thanks for tuning in. In any conductor there are charge carriers which are free to move, and if the 2 regions of a conductor are at different electric potentials, then charge will move from one region to another until the 2 potentials are the same. Now the art of charging conductors alters its potential in the region where it is charged. Now what does that mean? It means that having a charged conductor means that the charge redistributes itself, and as such, at equilibrium, every part of the conductor is at the same potential. Now if they are having the same potential, it means that the VDX will be constant, and so the intensity within a conductor will always be equal to 0. Hence, no electric field lies within the material of a conductor. Let's look at a few illustrations to further this point. If we look at these illustrations, we are having here a solid conductor, and this is a hollow one. In the solid conductor, we said that inside there is no field, the intensity is equal to 0, and the potential inside will remain constant. For a hollow conductor, we said that there is no charge that resides inside a hollow conductor. From our Faraday's experiments, that the tutorial we covered much earlier, no charge resides inside the hollow conductor according to the Faraday experiment, so meaning that the intensity inside the hollow conductor will be 0, but the potential difference will be constant. All the charge is residing outside the surface. So if we are to look at the variation of the intensity E and the potential V, this is how our graphs will look like. If looking at this graph here, we are having this axis representing the distance R from the center of the conductor, and here this is the intensity. So within the hollow conductor, within the solid conductor, the intensity will be 0. That is where our line there is moving at the 0 line. Then moving from outside the conductor onwards, our value of E will vary. The intensity will be inversely proportional to the square of the distance from the center, as shown. So down here is a variation of the distance R from it's the variation of the distance from the center of the conductor and the potential. And from here we see that the potential within the conductor is constant. The potential within the conductor is constant, but as you start moving out of the conductor, outside the conductor, the voltage, the potential is inversely proportional to the distance from O, from the center of the conductor. The same goes with when it is a hollow conductor. We have more or less similar diagrams like before. This is a graph showing the variation of the distance from the center and the intensity E, and the downer one is showing the variation of the distance from the center and the potential. This is quite similar to that for both the solid conductor and the hollow conductor. Simply subscribe to this channel if you want more of these tutorials, and for the benefit of your colleagues out there that would like to watch more of these tutorials, simply share this video. Speaking of surfaces that are having the same potential, it brings us to the concept of equipotential surfaces. Now, what are equipotential surfaces? These are two-dimensional surfaces which over the electric potential is constant, and it means that work done in moving a charge from one point of that surface to another is 0. If this was an equipotential surface, it would mean that the work done in moving a particle from this point to that point along the equipotential surface is 0. The direction of the force on an equipotential surface is always at right angles to the surface. And so if we were to, some of the properties of these equipotential surfaces is that the work done along the equipotential surface is 0. We also have another property that we should keep in mind, that the electric field intensity along the surface is always also 0, and also that the equipotential surface is at right angles to the lines of force. This brings us to the end of this tutorial. Thank you for watching. Simply subscribe to this channel for more, and for the benefit of your colleagues out there that would like to watch this tutorial, simply share this video. Otherwise, thanks for watching and hope to catch you in the next video. For Kisembo Academy, this is Arnold Rangakuramia. When taking a photo, the cameraman simply pushes a button and then comes a flash. Have you ever wondered how this photo flash comes about? Well, the photoflash is possible because of the storehouse of energy we shall call a capacitor. This device we are calling a capacitor is a storehouse of energy which releases the energy quickly during the short period of the flash. In this tutorial, we get to explore this device called the capacitor. Thanks for tuning in. This is Kisembo Academy. Now, what exactly is a capacitor? It is simply a passive two-terminal device which is used to temporarily store electrical charge. In our diagram here, we have a diagram of a capacitor. These are the two terminals we are talking about. Now, these two terminals are connected to two conductive plates. There is that plate that we are seeing on the top. There is that place that the plate at the bottom. And in between is an insulator. And this insulator is what we are calling the dielectric. Now, the dielectric material can either be air, it can either be paper, or it can even be oil. And then also, these metal plates can either be square, they can be circular, they can be rectangular, or they can even be cylindrical, all depending on its application and the voltage rating. This is the cross-sectional view of the basic structure of the capacitor, this being the dielectric and the two plates we are talking about. And then this is a schematic diagram. This is how it appears, the symbol, when you're drawing it in an electric circuit. So let's look at how we charge this capacitor. Now here, when we are charging a capacitor, we are having this diagram here that will become the basis for our explanations on how we charge and discharge a capacitor. In this, we have a resistor, we have an ammeter, we have the capacitor here, we have a source of voltage, which we've labeled V0. Then we have a switch. This switch key can either be connected to terminal 1 or terminal 2. When it is connected to terminal 1, it would mean that the circuit is like that. So it would mean that if switch key is connected to terminal 1, it means this lower part of the circuit is out. Then if we connected this switch key to terminal 2, it would mean this upper part of the circuit is out, and we only have that one down. So we are going to look at how both work out. When we want to charge this capacitor, it means we are going to connect it to terminal 1 so that it gets charged. It gets its charge charged with electrons being put. It gets charged when it is connected to terminal 1 because it's in the upper circuit that we are having a source voltage. Now, if you want to discharge this capacitor, we will connect it to terminal 2 and it will get discharged. Now, let's exactly explain what happens during the charging process and the discharging process. So, we will begin with the charging process. The charging process is when we connect switch K to terminal 1, and that is it's what we have here. This is switch K according to our diagram. Switch K has been connected to terminal 1, that's it. This is the switch K we are talking about. It has been connected to terminal 1, and so that means that the lower circuit is out of the picture. Explaining the charging process. Now, electrons flow from the negative terminal of the battery, which is that one, to this plate Y. Why do they flow? Of course, this being negative terminal, the electrons will be repelled. And when they are repelled, it means they are going to concentrate on this plate, and so this plate Y will become negatively charged. Likewise, this being a positive terminal of the battery, it is going to attract electrons from this plate X. And so electrons will be attracted towards the positive terminal and leaving an excess of positive charges here. So it means that plate X becomes positively charged, plate Y becomes negatively charged. Now, as these charges accumulate on these plates, the potential difference across these plates starts increasing. Now, as the potential difference across these plates increases, the amount of current that is going to be flowing through the ammeter also starts decreasing. So it is such that when the potential difference across this plate increases to the point whereby the PD across these plates of the capacitor is equivalent to the PD across the cell, then it would mean that this capacitor has been fully charged, and so there will be no flow of electrons. I mean, the flow of electrons will cease. This is explained in our graph of current against time. When we look at this graph of our current against time, initially the current is very high. The flow of electrons, or the current from the cell, is very high. But as the charging process continues, the amount of current goes on decaying as the potential difference across the plates of this capacitor gets on increasing. So the current decreases up to 0. So it means that at this point in time, it means that the potential difference across the plates of the capacitor is equivalent to the potential difference or the EMF of that cell. And so at that point, the charging of this capacitor has been complete, and so no current flows. Let's look at how the potential difference across the capacitor plates varies with time. When we are charging this capacitor, the PD across the plates of this capacitor at first is 0. So as the charging continues, the PD across this capacitor increases, and as it increases, it reaches the maximum. It reaches the maximum voltage and the charging stops. The charging gear is going to be, the capacitor will be fully charged when the potential difference across this cell is equivalent to the EMF of that cell. And at that point, current stops flowing. The ammeter is no longer deflecting, meaning current is not flowing anymore. Now let's explain the discharging process. Looking at the discharging process, we are now connecting switch K. Previously switch K was being connected to point 1. Now we are connecting switch K to terminal 2. That is what we are seeing here. Switch K is being connected to terminal 2. When switch K has been connected to terminal 2, remember, in this part of the circuit there is no source of EMF. We are just having two plates that are charged that are being connected to a resistor and to some circuit. So when that happens, it means electrons are going to flow from plate Y, and they will flow to come and discharge this plate X. So what does that mean? It means that the potential difference across the capacitors at first is very high, but as these electrons flow from plate Y to come to discharge or to neutralize plate X, it means that the potential difference across this capacitor will decrease. When the potential difference across this capacitor decreases, it means that this capacitor is also going to lose its energy. So that is how it gets discharged. Looking at the current also flowing through this ammeter at first is high when the electrons are traveling to come and discharge the X plates, but as time goes on, the current decays to 0, and when the current that is flowing through the ammeter decays to 0, it would mean that the capacitor has been fully discharged. Let's look at how these parameters vary on the graph. Looking at the voltage against time, we said that during the discharging process, at first when we connect switch K to 2, the voltage is very high. Then these electrons start flowing to come and neutralize the positive charges on the X plate. So when that happens, the voltage starts dropping up to when the voltage decays to 0. And when the voltage decays to 0, it means that the capacitor has been completely discharged. Let's examine how current is going to vary during the discharging process. Now during the discharging process, when the voltage again across this is too high, it's going to mean that the current that is going to flow will be high at first. But then as time goes on, the current is going to be very high, but this flow of current is in the opposite direction. Remember, previously, during the charging process, if this is the outflow of electrons, it means that our current flows in the opposite direction to flow of electrons. So current was flowing in that direction through the ammeter. It was entering the ammeter from this side, moving like that, the flow of current. That is charging. Now when we changed the terminals and we connected it to terminal 2, that is now during the discharging process, it means that the electrons on this plate are going to travel in this direction, meaning current will travel in the opposite direction. So it means that when we are plotting according to our graph, the current is first going to be high but it is traveling in the negative direction. That's why the graph is at the negative part. But then as these electrons move and continue to neutralize this plate, it will decay to zero. So that's all about the discharging process of a capacitor. R times C is going to give us a certain constant we are going to call the time constant. Now, this constant is what categorizes, or what characterizes the rate of charging and discharging of the capacitor. So it means that if R, or the resistance that is in the circuit, is small, or if the capacitance of the capacitor in the circuit is small, it means that this constant here is going to be small. And if that constant is small, it means that the rate of charging and discharging of the capacitor will be faster. If the resistance is very high and all the capacitance is also very high, it means that if we multiply those two, it's going to give us a time constant that is very high. So when the time constant is very high, it's going to simply mean that the rate of charging and discharging of that capacitor is going to also be, it's going to be slow. So if you want to watch more of this video, I encourage you to subscribe to this channel, and for the benefit of your colleagues out there that would like to watch more of these tutorials, simply share this video. Otherwise, thanks for watching, and hope to catch you in the next video. For Kisembo Academy, this is Arnold Ranga Kurambi. In our previous tutorial, we introduced the capacitor, a temporary energy storage device. The measure of its capacitance to store a charge is what we shall refer to as capacitance, and that's what we shall discuss in this tutorial, along with other factors affecting capacitance of a capacitor. It's Kisembo Academy, and thanks for tuning in. Now, the capacitor, as you know, it has the capacity to store energy in form of an electric charge, thereby producing a potential difference across its plates. So you can think of a capacitor as more like a small rechargeable battery. By applying a voltage to a capacitor and measuring the charge on the plates, the ratio of the charge, which we shall call Q, to the voltage, or what we will call the potential difference, will give you the capacitance value of the capacitor, and is therefore given as capacitance is going to be equal to Q, which is the charge on the plates, on either plates of the capacitor, divide that by the potential difference across the plates of the capacitor. The property of a capacitor to store a charge on its plates in form of an electrostatic field is called the capacitance of a capacitor. Now, although sometimes we may say that this charge is, or the energy that is stored by the capacitor is stored on the plates of the capacitor, but it is more realistic, it is more truthful to say that actually the energy is stored within the field between the plates of the capacitor. That's where the actual energy is stored. So by definition, we can say that capacitance is defined as being the ratio of the magnitude of the charge on either plates of a capacitor to the potential difference, or the PD, across the capacitor. Or you can say that capacitance is the electrical property of a capacitor and is the measure of the capacitor's ability to store an electrical charge on its two plates. And looking at this, we know that capacitance is going to be Q. Q is measured in coulombs. The SI unit for voltage is volts. The SI unit for capacitance is farads. And we know that 1 farad is 1 coulomb per volt. So in other words, if you are to define what exactly a farad is, you would say that a farad, or 1 farad, is the capacitance of a capacitor when charged with 1 coulomb, with the potential difference across its plates being 1 volt. So we get to look at the factors that are affecting capacitance of a capacitor. We have basically 3 factors that affect the capacitance of a capacitor. We'll discuss them one by one. We have the first one being the distance of separation between the plates. We have the area of overlap, and then the permittivity of the dielectric. If we're looking at, we shall use this illustration. We have a source of PD here. We have 2 plates. We'll call this plate P and plate Q. This plate is connected to a gold leaf electroscope. and we are going to use the gold leaf electroscope to tell us the charge. It will be a measure to tell us whether the capacitance of the charge on this plate is increasing or decreasing. If the charge on this plate increases by show of divergence of this gold leaf electroscope, it would mean that the capacitance has also increased, and vice versa. This D shows the distance of separation between the two plates. So we shall begin with the distance of separation between the two plates. How does that affect the capacitance of a capacitor? Now we set up our diagram here, and what we have this plate P and plate Q with the distance of separation D in between them. So what happens is that when we try to bring the plates together, it means we are reducing the value of D. So when we reduce the value of D, or when the plates are brought together, it means that experimentally, the gold leaf electroscope, the leaves of the gold leaf electroscope will diverge, meaning that there is more charge that is accumulating on this plate as a result of bringing the plates together. So what does this mean? It means that when the value of D is decreasing, or when you bring the plates together, it means that the capacitance of this capacitor is increasing. Likewise, if you take those plates apart and you try to pull them apart, this gold leaf will drop. The divergence of this gold leaf will drop, which is a sign that when you increase the distance of separation between the plates, the capacitance of the capacitor will drop. So it brings us to the conclusion that the capacitance of a parallel plate capacitor is inversely proportional to the distance between the plate, or the separation of the plates. So that is one factor that affects the capacitance of the capacitor, and that is the relation we get out of it. We'll get to look at the other factor, the area of overlap. This is a piece of paper, and this is another piece of paper of different color. So it means that the area of overlap. This demonstration serves to illustrate what I mean by area of overlap. Looking at your screen are two papers that are overlapping each other. In this case, we assume that these two papers are two plates of the capacitor P and Q. When they overlap each other, the area of overlap is what you see as the region that is darker in the middle of the two overlapping papers. So when the darker region increases in area, it means that the area of overlap has increased, and vice versa. So relating this to the capacitor plates P and Q, if you move the two plates relative to each other, the area of overlap will vary. An increase in area of overlap will cause the gold foil in the gold leaf electroscope to increase, which means an increase in capacitance. And a decrease in the area of overlap will mean a decrease in the divergence of the gold foil, and therefore a decrease in the capacitance of the capacitor. This simply brings us to the conclusion that the capacitance of a parallel plate capacitor is directly proportional to the area of overlap. If we introduce a dielectric in between the plates of the capacitor, it's going to increase the capacitance of that capacitor, and if we do not introduce a dielectric in between the plates, it's simply going to mean that the capacitance of the plate will be less. Let's examine the effect of a dielectric on the capacitance of a capacitor, or a parallel plate capacitor. Now when we put a dielectric between a parallel plate capacitor into the gaps of a parallel plate capacitor, how does this dielectric affect the capacitance? Now here we are having a capacitor with two plates. This is a negatively charged plate, and this is a positively charged plate. There is no dielectric in between the plates. So it means that in between the plates there is a field, and this field is acting in that direction, and we have called that field EO, subscript O. That's the field between the plates. Now we are going to introduce a dielectric in between these two plates. Now when we introduce a dielectric or an insulator in between the plates, what happens? Initially, this dielectric has got its molecules inside it that are random. But then when we introduce these molecules into this field E0, these molecules are going to be polarized. So when they are polarized, you'll find that near the surface of the dielectric, the surface that is next to the positive plate, we shall have molecules that are polarized in such a way that we are having a negative terminal. Negative electrons will be attracted at this end. Likewise, on the negative plate, near the surface, we'll have positive charges on the surface of the dielectric. So what does this mean? It means that we are having now two fields. We have a field that is due to the plates, and then now we are having a field that is being brought about by the polarization of the dielectric. But the field that is being brought about by the polarization of the dielectric is acting in the opposite direction to the field due to the plates. How? We all know that the field moves from positive to negative. This is the positive plate, that's the negative plate. And so the field due to the plate is going to move from this direction in that direction. And we are calling that field E naught. But then when we introduce the dielectric in between the plates, and we find that this positive induces a negative charges on the surface of this dielectric as a result of polarization of the molecules inside the dielectric. Likewise, this negative is going to induce a positive charge on the surface of the dielectric. So it means that you're having a dielectric that is polarized with a negative on the surface this way and the positive on the surface that way. So what does that mean? It means that there's going to be a field that is created in between the plates, which we are calling EP. But this field is acting in the opposite direction to this one, the field due to the plates. Because this EP is from positive to negative, so the field acts in that direction. So what does that mean? It means that we are having two fields. We are having a field acting in that direction. We are having another field in the same space that is acting in the opposite direction. So it means at the end of the day, we are going to get a resultant field as a result of these two. So the resultant field we get after this field cancels out with that one is going to be less than the actual field that is supposed to be here. So how does this affect the capacitance of this capacitor? That's what we seek to explore. We see that the field due to the plates E naught minus the field due to the polarization of the molecules, which we are calling EP, is going to give us a resultant field ER. Of course, this effective field ER will be less, much less. So after getting that effective field ER, which is much less, from the equation for intensity of the parallel plate capacitor, E is going to be V over D. Getting the voltage here, making V the subject of the formula, we know that the voltage is going to be equal to E times D. Now, since E is going to reduce, since the effective field or the effective intensity is going to reduce, it means that the value of V will reduce. I mean, if you look at this expression, the voltage between the plates is going to be equal to the intensity E times D. And we are having the intensity reducing because of this. So when the intensity reduces, it means that the amount of voltage between the plates is also going to reduce. So when V also reduces, how does that affect the capacitance? We know that capacitance is the charge per unit potential difference across the plates, like we have seen here. Capacitance C is going to be the charge per unit PD. Now, if this value of V has reduced, it means that it's going to increase the value of C. So since V reduces, capacitance will automatically increase. And so that is how the capacitance is affected by the dielectric. So meaning that if you introduce the dielectric in between the plates of a parallel plate capacitor, it's going to increase the capacitance. And that brings us to that conclusion that the capacitance of a capacitor C will increase with the existence of a dielectric. So the three factors will bring us to this relation, that capacitance of a parallel plate capacitor is inversely proportional to the distance between the two plates, but it will be directly proportional to the area of overlap between the plates, and it will also be directly proportional to the permittivity of the dielectric that has been introduced in between. And that brings us to that relationship, which has been, these are the three factors that affect the capacitance of a parallel plate capacitor: the dielectric constant, the area, and the plate separation. In our next tutorial, we shall look more into the capacitance of a parallel plate capacitor, and with a specific interest on how we arrive at this expression arithmetically. Thank you for watching this video. I encourage you to subscribe to this channel if you would like to watch more of these tutorials. Otherwise, for the benefit of those your colleagues out there who would like to watch this tutorial, simply share this video. Otherwise, thanks for watching, and hope to catch you in the next tutorial. For Kisembo Academy, this is Arnold Ranga Kuramia. We said that Gauss theorem simply states that the total flux that is passing normally through any closed surface, whatever its shape, is always equal to Q over E. That's the flux we're talking about. It states that the total flux passing normally through any closed surface, whatever its shape, is always equal to Q over E, where Q is the total charge and E is the permittivity. Now, we can express Gauss theorem in terms of surface charge density. This is Gauss theorem. We can also express it in terms of surface charge density. How? We know that flux is equivalent to the intensity of the field, multiply that by the area through which the field is going. This area has to be normal to the field. And if the area is not normal to the field, then we're supposed to resolve the field to the normal, or to the perpendicular line that is going through the area, like we earlier described. So flux is the intensity times the area, and that is going to be equal to the charge times, divide that by the permittivity. Now, dividing area on both sides so that we have the intensity on one side, we have A coming down here. But then we know that the charge per unit area is what we know as charge density, denoted by that. So in simple terms, this intensity can also be equal to charge density, divide that by permittivity. Now, finding the expression whereby you are having intensity is equal to charge density, divide that by permittivity, this is actually coming from Gauss theorem. Capacitance of a parallel plate capacitor. Now, for us to get the expression for the capacitance of a parallel plate capacitor, we are going to get that from Gauss theorem. And from Gauss theorem, it's where we get this expression that E is going to be equal to the charge density, divide that by the permittivity. But we know, the surface charge density, or we know that the charge density, which is this is surface charge density. But we know that the surface density, or the charge density on the surface of these plates, is equivalent to the charge on those plates, which is Q, divide that by the area, as shown here. The surface charge density is equal to Q over the area. So we substitute this in that expression. So when we substitute this here, it means that our value of E is still going to be Q over A, which is that one, the surface charge density, divide that by the permittivity of the field, which is that. So we'll end up with our expression for intensity E, which is going to be equal to Q, which is the charge on either plate, divide that by the permittivity times the area on the surface area of the plates. But since we are dealing with parallel plate capacitors, we know that the intensity of two parallel plate capacitors, E, is equivalent to the PD between the plates over their separation, V over D. So we are supposed to substitute for the value of E, we put V over D, because this is the expression for intensity. This is the expression for the intensity of the field between two parallel plates. And we also know that for capacitors, the amount of charge that is residing between two capacitors is equivalent to the product of the capacitance multiply that by the potential difference between the two capacitors. So Q is equal to CV, we substitute it there. So when we substitute this here and this one there, we end up with an expression that has gotten C in it. So substituting gas gives us an expression with C in it, and when we make C the subject of the formula, we come up with C being equal to permittivity times the cross-sectional area, divide that by the distance of separation between the two plates. And this is the formula or the expression we use when we are trying to find the permittivity, when we are trying to find the capacitance of a parallel plate capacitor. This brings us to the end of this video. Thanks for watching. For more of these videos, simply subscribe to this channel. Otherwise, for the benefit of your colleagues out there that would like to watch this tutorial, I would encourage you to share the video. Otherwise, thanks for watching and hope to catch you in the next video. For Kisembo Academy, this is Arnold Ranga Kuranyo. The formula you're seeing on your screen is the formula we use when we are trying to find the capacitance of a parallel plate capacitor. And we said that capacitance of a parallel plate capacitor is equivalent to the permittivity. Multiply that by the cross-sectional area of the plates, the area of either plates, divide that by the distance between the two capacitors. Now, we have two capacitors here. We have a capacitor that does not have a dielectric between its plates, and we have a capacitor that has got dielectric between the plates. Now, we said that a dielectric is an insulator, and it can either be water, it can be oil, it can be air, but that is a dielectric for you. Now, if we got using the previous formula, if we got the capacitance, we can calculate the capacitance of this capacitor. We can also calculate the capacitance of that capacitor without the dielectric. Now, when we get the capacitance of those two capacitors and we find their ratio, we are going to get a terminology we shall call the relative permittivity. Now, what is relative permittivity? It is simply the ratio of the capacitance of the capacitor when there is a dielectric in between the plates to the capacitance of the capacitor that does not have a dielectric in between its plates. In other words, defining it, the relative permittivity is the ratio of the capacitance of a capacitor with the dielectric. Relative permittivity is the ratio of the capacitance of the capacitor with the dielectric between the plates to the capacitance of the capacitor when there is no dielectric between its plates. The relative permittivity is going to be equal to the capacitance of the capacitor when there is a dielectric in between, which is that, to the capacitance of the capacitor when there is no dielectric in between, and that is going to be equal to, this is the capacitance of the capacitor when there is no dielectric in between, which is the permittivity of that dielectric multiplied by the area, divide that by the distance of separation between the two, divide that by the capacitance of the same capacitor when there is no dielectric in between. And when there is no dielectric in between, we are having epsilon naught, the permittivity of free space, multiply that by the area of the same capacitor, divide that by d, the distance of separation. So when we divide those two expressions, we shall end up with a ratio when the permittivity of the dielectric to the permittivity of free space. So meaning that is the expression for relative permittivity. So in other words, this brings us to a conclusion that the relative permittivity is the ratio of the permittivity of a substance, which is that this is the relativity of a substance, to the permittivity of free space. And permittivity of free space is what has been denoted as by epsilon naught. And then 2, relative permittivity has no units, and relative permittivity of free space is always equal to 1. Dielectric strength. Let's look at this more like tensile strength, or you're having a material and you have loaded it with some bit of load. Of course, if the material is elastic, it will endure, it will keep extending, it will be extending because it is elastic, but then it will reach a point whereby it won't be elastic anymore. It can't stretch anymore, and as a result it loses its elasticity and it breaks, or it loses its elasticity, and if you continue imposing that load on it, it will eventually break. That is in mechanics. Now relate that to this dielectric strength. We have dielectric, sometimes we shall put these insulators we call dielectrics in between the plates of a parallel plate capacitor. Now these insulators also have got strength, a limit to their strength. So now if we are defining what dielectric strength is in simple terms, we shall simply say that it is the measure of the electrical strength of a material as an insulator, or we can say that the electric strength is defined as the maximum voltage that is required to produce a dielectric breakdown through the material, and this voltage that is required to break down this insulation is expressed in terms of volts per unit thickness. So in simple terms, you can say that the maximum voltage that can be applied to a material before it breaks down is what we are calling dielectric strength. And by definition, we can also refer to it as the potential gradient at which the insulation of the dielectric material breaks down and the spark passes through it. Let's examine the effect of a dielectric on the capacitance of a capacitor or a parallel plate capacitor. Now when we put a dielectric between a parallel plate capacitor into the gaps of a parallel plate capacitor, how does this dielectric affect the capacitance? Now here we are having a capacitor with two plates. This is a negatively charged plate and this is a positively charged plate. There is no dielectric in between the plates. So it means that in between the plates there is a field, and this field is acting in that direction, and we have called that field EO, E subscript O. That's the field between the plates. Now we are going to introduce a dielectric in between these two plates. Now when we introduce a dielectric or an insulator in between the plates, what happens? Initially, this dielectric has got its molecules inside it that are random. But then when we introduce these molecules into this field E0, these molecules are going to be polarized. So when they are polarized, you'll find that near the surface of the dielectric, the surface that is next to the positive plate, we shall have molecules that are polarized in such a way that electrons will be attracted at this end. Likewise, on the negative plate, near the surface, we'll have positive charges on the surface of the dielectric. So what does this mean? It means that we are having now two fields. The first, we have a field that is due to the plates, and then now we are having a field that is being brought about by the polarization of the dielectric. But the field that is being brought about by the polarization of the dielectric is acting in the opposite direction to the field due to the plates. How? We all know that the field moves from positive to negative. This is the positive plate, that's the negative plate. And so the field due to the plate is going to move from this direction in that direction. And we are calling that field E0. But then when we introduce the dielectric in between the plates, and we find that this positive induces a negative charges on the surface of this dielectric as a result of polarization of the molecules inside the dielectric. Likewise, this negative is going to induce a positive charge on the surface of the dielectric. So it means that you're having a dielectric that is polarized with a negative on the surface this way and the positive on the surface that way. So what does that mean? It means that there's going to be a field that is created inside, in between the plates, which we are calling EP. But this field is acting in the opposite direction to this one, the field due to the plates. Because this EP is from positive to negative, so the field acts in that direction. So what does that mean? It means that we are having two fields. We are having a field acting in that direction. We are having another field in the same space that is acting in the opposite direction. So it means at the end of the day we are going to get a resultant field as a result of these two. So the resultant field we get after this field cancels out with that one is going to be less than the actual field that is supposed to be here. So how does this affect the capacitance of this capacitor? That's what we seek to explore. We see that the field due to the plates E0 minus the field due to the polarization of the molecules, which we are calling EP, is going to give us a resultant field ER. Of course, this effective field ER will be less, much less. So after getting that effective field ER, which is much less, from the equation for intensity of the parallel plate capacitor, E is going to be V over D. Getting the voltage here, making V the subject of the formula, we know that the voltage is going to be equal to E times D. Since the effective field or the effective intensity is going to reduce, it means that the value of V will reduce. I mean, if you look at this expression, the voltage between the plates is going to be equal to the intensity E times D. And we are having the intensity reducing because of this. So when the intensity reduces, it means that the amount of voltage between the plates is also going to reduce. So when V also reduces, how does that affect the capacitance? We know that capacitance is the charge per unit potential difference across the plates, like we have seen here. Capacitance C is going to be the charge per unit PD. Now, if this value of V has reduced, it means that it's going to increase the value of C. So since V reduces, capacitance will automatically increase. And so that is how the capacitance is affected by the dielectric. So meaning that if you introduce the dielectric in between the plates of a parallel plate capacitor, it's going to increase the capacitance. And that brings us to that conclusion that the capacitance of a capacitor C will increase with the existence of a dielectric. Thanks for watching. If you want more of these videos, simply subscribe to this channel. Otherwise, for more videos, simply subscribe to Kisembo Academy. For the benefit of your colleagues out there who would like to watch this tutorial, simply share the video. Thanks for watching. Catch you in the next video for Kisembo Academy. This is Arnold Ranga Kuramya. So in this session, we are going to simply show how we can measure the capacitance of a parallel plate capacitor, like you're seeing, using a reed switch. So that's the setup of the apparatus, and what we essentially need to do here is to switch on our reed switch. This right here is a reed switch whose frequency is known. So we connect our apparatus like that, and then we switch on our reed switch. What happens is that every time this reed switch touches terminal A, this circuit here is completed, and when this circuit right here is completed, the capacitor is charged. So since this capacitor here is connected to that battery right there, and definitely here we have a voltmeter to measure the voltage. And so once this touches B, when this switch touches B, it means this side of the circuit is disconnected. So when it touches B, the capacitor is disconnected, and the capacitor is disconnected from this part of the circuit. So it's this circuit that gets into force. That is, if this touches B, when the switch touches B, it means the capacitor gets discharged, and as it's getting discharged, we're able to get the current while this capacitor is being discharged. In other words, this is what happens, is that when this is connecting to here, when the reed switch connects to point A, the capacitor charges and then when it connects to B, the capacitor discharges. And in both cases, while the capacitor is charging, we are able to get the potential difference across the capacitance. Then when the capacitor is discharging through B, we are able to get the amount of current that during the discharging process, and that is measured by the milliampere right here. The readings on the voltmeter and the milliampere are noted. When these readings are noted, we need to take note that each time the capacitor charges, we know that the charge that is gained during the charging process given by the capacitance of that capacitor, multiply that by the potential difference. Then also each time the capacitor discharges, we are able to know the amount of current that is flowing through the milliampere during that discharging process, and it's given by current, it's given by the charge, divide that by the periodic time. Now I use periodic time because as far as we are concerned, the reed switch we are using is a reed switch whose frequency is known, and so if we are using periodic time, remember that this, we know that periodic time can still be given by 1 over that frequency that we know. So what is our aim here? Remember, our aim here is to find the capacitance of this capacitor using this reed switch. So from here we can play around with these two with these two expressions to get ourselves the value of C. So to get the value of C here, which so happens to be the capacitance, we know V. We are getting V from the experiment here. Yeah, then we do not know the value of Q, but we can substitute it using this expression. So if I may rewrite this, this will mean so looking at this, we know that Q is equal to C V. We are interested in finding the capacitance of that capacitor, so when we make C the subject of the formula, C is giving us the Q, the charge, divide that by the voltage. Now the voltage we know because we are able to get that from here, but we do not know the charge Q, but we can substitute this value of Q using this expression. Let me try and rewrite this expression back here. This, we know that the current flowing is given by Q over periodic time T. Let me make Q the subject of the formula. Q is going to be given by the current times the periodic time. And I know we do not know the periodic time, but we know that current times periodic time is given by 1 over F times 1 over F, means that our value of Q here now becomes I over F. That is current divided by the frequency of the reed switch. So it means we can now go ahead and substitute this value of Q right there. So when you substitute it right there, we will end up with our expression for capacitance being as, you know, I divide that by VF, where I is the current that we are getting from the milliampere, and then the voltage is what we are getting here, and also the frequency, that is the frequency of the reed switch. So with that, we are able to find the capacitance of a capacitor using a reed switch circuit. So in this session, we are going to measure the dielectric constant of a capacitor using a calibrated gold leaf electroscope. Now, we should all remember that a dielectric constant, by definition, we know that a dielectric constant is simply referred to as the ratio of the permittivity of the material that is always between the plates of a capacitor to the permittivity of a vacuum. But also another definition for dielectric constant is that dielectric constant is equal to the ratio of the capacitance of a capacitor with the dielectric between its plates to the capacitance of the same capacitor with the vacuum between its plates. In our previous sessions in this series of electrostatics, we were able to explore that in more detail. So we are going to use this circuit to measure the dielectric constant using a calibrated gold leaf electroscope. So let's get to it. So this gold leaf electroscope you're seeing here is calibrated so that it is able to measure electric potential. Yeah. So this simply means that the divergence of that gold leaf is supposed to be dielectrically proportional to the voltage. In other words, the angle of deflection is supposed to be directly proportional to the voltage that it's measuring. So that is why we have here that the voltage that this thing will be measuring should be directly proportional to the angle of deflection. And of course, if we are to remove that, that proportionality sign, we end up with a constant of proportionality k. So that's how we end up with V is equal to k theta. So what happens here is that we are going to first close switch k while keeping k2 open. We close switch k1 while keeping k2 open. Of course, when we close switch k1, it means that this capacitor is going to be charged, because this is the only circuit that will be in play. And so when this capacitor is charged, afterwards then we shall open k1 and then we shall close switch k2, and then we shall close switch k2 while k1 is open. It means that the charge that is inside this capacitor is going to cause this to be deflected. So when it is deflected, it means that the voltage that we are supposed to get from this is equal to k times the deflection, which we've called theta 1. This is coming directly from that. Now for V1 is equal to k times theta 1, we are doing this, we are closing k2 while the capacitor has no dielectric between it, or when it is a vacuum, or when there is nothing between the plates. So again, without discharging the capacitor and without, changing the distance of separation, we insert a dielectric between the, the power plate capacitor, and again, we close switch K2, and we are able to get, so we shall go and read off another value of theta when we have inserted the dielectric between the power plate capacitor. That is done without altering, the distance between the two plates and without discharging this capacitor. So we insert a dielectric between the the power plates of the capacitor, and we are able to read another value of theta, which we are calling theta 2, and so we are able to come up with this expression of the voltage. V2 is equal to k times theta 2. So of course, after coming up with these two expressions, our interest here is that we are interested in finding the dielectric constant. And remember, we said by definition that the dielectric constant can be defined by the ratio of the permittivity of this dielectric to the permittivity of free space, or the permittivity of the vacuum. It can also be defined as the capacitance of a capacitor when there is a dielectric between its plates, to the capacitance of a capacitor when there is no dielectric between the plates, or in other words, when there is a vacuum between the plates. So from this, we are simply going to use the second definition. We are going to find the expression for the capacitance of a capacitor when there is a dielectric between the plates, to the capacitance of the capacitor when there is no dielectric between the plates. So we all know this expression. We know that charge of a capacitor is given by C times V, C being the capacitance of the capacitor, V being the voltage across that capacitor. Now, when we're carrying out this expression, the charge between the plates of that capacitor is the same in both cases here. So going to case 1, when there was a vacuum between the plates, that is in the first instance, we know that Q is given by the capacitance of that capacitor, which we are calling C times V, and in this case the V is this, so Q times V1, which is going to be Q is equal to the capacitance of the capacitor when there was no air, that is C1 times V1, which is K, which is times K times theta 1. Okay, so that is equation 1. Then let's do the same case for the case when there is a dielectric between the two plates of the capacitor. When there is a dielectric between the two plates of the capacitor, we shall simply come here and say that the charge is between the capacitor, the power plates of the capacitor is given by the capacitance of the capacitor when there was a charge between the two plates, multiply that by the voltage, V2. And in this case, this is going to become, Q is going to be C times V2, which so happens to be K times theta 2. Like that. So this is going to become our equation 2. right there. So what happens is that we are going to divide this equation and that. In other words, we are going to say, so equation 2, divide that by equation 1 is going to be given by, equation 2 is this, so it's going to become Q, which is going to be equal to this, C2 times K times theta 2, divide that by equation 1, which is right there, which is Q is given by C1, this is 1, K times theta 2. I'll continue with the working here. This Q divided by that Q gives us 1 is going to be equal to, then this C2 over C1, that's going to be C2, divide that by C1. This constant will cancel out, then we shall remain with theta 2 over theta 1 times theta 2 divided by that by theta 1. Let's make this a flat equation. Well, we can multiply the denominators on both sides times C1 theta 1, C1 theta 1. This goes with that, you remain with C1 theta 1, giving you C2 theta 2. So let's keep the C's. You remember C1, C subscript 1 is the capacitance of the capacitor when there is no dielectric. C2 is the capacitance of the capacitor when there is a dielectric. So if we can simply say over C1 here, over C1, so that you know this goes with that, then we do this over theta 2 over theta 2, so that this goes with that, you shall remain with theta 1 over theta 2, giving us C2 over C1. Remember, C2 is the capacitance of the capacitor when there is a dielectric between the plates. C1 is the capacitance of the capacitor when there is no dielectric between the plates. And by definition, we know that the dielectric constant is given by the capacitance of the capacitor when there is no dielectric, the capacitance of the capacitor when there is a dielectric between the plates, to the capacitance of the capacitor when there is no dielectric between the plates. And this ratio is the same as the deflection that you get when there is no dielectric between the plates to the deflection that you get when there is a dielectric between the plates. So in other words, when we do this experiment right here using this setup and we want to measure the dielectric constant using a calibrated gold leaf electroscope, if we simply get the ratio of the angle or the deflection when there is no dielectric between the plates to the deflection when there is a dielectric between the plates, this ratio is able to still get us the dielectric constant. And so that enables us to find the dielectric constant using a calibrated gold leaf electroscope.
Just like resistors, capacitors can also be arranged either in series or in parallel. Today, we get to look at how these capacitors and capacitors are arranged. So let's look at capacitors in parallel. When capacitors are arranged in parallel, the key, just like in resistors, the potential difference across these capacitors in parallel is the same. Just like in resistors, the potential difference across resistors in parallel is the same. Now, on all these plates, there is a positive and negative induced on either plates. From this side, for example, looking at this negative terminal, all the electrons from here will be repelled. When these electrons are repelled, they reach this junction, and when they reach this junction, they are redistributed. They are distributed to C1, to C2, to C3. And so it means that negative charges are induced this side. So looking at it from this side of the capacitors, this is a positive terminal of the cell. So it means this positive terminal of the cell is going to attract electrons from these terminals. When these electrons are attracted from these terminals, they are going to be attracted in that direction. Electrons will flow in this direction. So when the electrons flow in that direction, it means that we are going to have a negative. We are having positive plates this side and unequal but opposite negative charge is going to be induced on these plates. And these are the charges we are calling Q1, Q2, and Q3. So for the current that is inducing this is the same, it's coming from this. It means that for us to get the total charge that is induced here, Q1, plus the charge that is induced here, Q2, plus the charge that is induced here, Q3, is going to be equal to the total charge in the whole circuit, because the total charge is being induced by the same current. So the total charge that would have been induced by this same current that is traveling here from positive to negative is going to be equal to the charge that has been induced here by that current that has been split due to Q1, Q2, and Q3. So in essence, or in other words, the total current in this, the total charge in this whole circuit, capital Q, is going to be equal to Q1 plus Q2 plus Q3. But we all know that Q is going to be the capacitance of the capacitor, C times the voltage. So Q1 is going to be C1 times V, Q2 is going to be C2 times V, Q3 is going to be C3 times V. We notice that the V's are the same. Why? Because we said that because the capacitors are in parallel, their potential difference is the same. So the potential difference is the same, and so these V's will cancel out, and we'll find that we'll remain with an expression for capacitance of capacitors in parallel being C being equal to C1 plus C2 plus C3. Now let's get to look at capacitors that are in series. Now for capacitors that are in series, they have more or less a source of voltage V0, and that is how they are positioned. Now we are going to have the same current. Just if these were resistors, it would mean that we are having the same current traveling from the positive terminal moving through. It's the same current all through. That's the key. So here, and with resistors, we said that it's going to be the same current. It means it's going to be the same even with capacitors. It's going to be the same current moving through. So it means that as this current is moving through, it's come here, this being the positive terminal, electrons are going to be attracted from this, and when these electrons are attracted, they are going to induce a positive charge there. Positive charges will be left here as electrons are attracted towards the positive terminal of the cell. So when a positive charge is induced here, unequal but opposite charge is induced on the other plate, which is the negative. Same here, a positive charge is induced here, unequal but opposite charge is induced in the other plate. A positive charge is induced here, unequal, and opposite charge is induced there. And the chain continues. This being a negative charge, it's going to repel electrons and that are going to come to this plate, making it predominantly negatively charged. So what does that mean? It means that the charge in this capacitor is going to, the value of that is the value of Q, is going to be equal to the charge in this capacitor, which is the same as also the charge in that capacitor, the value of Q. But then the potential difference in the whole circuit, which is V0, is going to be different. For us to get the total potential difference in this whole circuit, V0, it's going to be equal to the potential difference across the first capacitor plus the potential difference across the second capacitor plus the potential difference across the third capacitor. It is just like when we are trying to find the total voltage in a circuit where there are resistors. The total PD, or the EMF of the cell, is going to be equal to the EMF of the resistor 1 plus resistor 2 plus resistor 3. That is when you're trying to find the total PD for resistors that are in series. So there's a relationship here. It's the same with capacitors in series. So what does that mean? So this will be our beginning point, that for us to get the potential difference in this whole circuit, it's going to be the potential difference across the first capacitor plus the potential difference across the second capacitor plus the potential difference across the third capacitor. And that is what we have done here. V0 is going to be equal to VA, which is potential difference across the first capacitor. We've called it VA, plus the potential difference across the second capacitor plus that across the third. But from our formula, that charge is going to be equal to CV0 meaning if we make the V the subject of the formula, it will mean that our value of V, the potential difference, is going to be equal to the charge Q over C. So we substitute this in this expression. So we'll end up with V naught, which is the charge in the whole circuit, divide that by the effective capacitance of the entire circuit, is going to be equal to Q, that is the charge in the charge in the first capacitor, over C1 plus Q over C2 plus Q over C3. This is C1, C2, C3. Now, like we had said, that the charge in all these is the same. It's the same charge that is induced throughout the whole circuit. So that's why the Q's are the same, but the C's are different. We have C, C1, C2, C3. So the capacitances are different. So these Q's will cancel out since they are the same, and we'll get an expression for the effective capacitance of the capacitors in series as being 1 over C, being equal to 1 over C1 plus 1 over C2 plus 1 over C3. So these things have a relationship. This brings us to the end of this video. Thank you for watching. For the benefit of your colleagues out there who would like to watch this tutorial, simply share. If you want more videos, I encourage you to subscribe. Otherwise, thanks for watching and hope to catch you in the next tutorial. For Kisembo Academy, this is Arnold Rangakuramya. We are required to calculate the charge on C1 and C2 and the PD across each. So we are having two capacitors here. We want to find the charge that is on these capacitors C1 and C2. Let's call this C1, let's call this C2, and we are required to find the charge on both of them. Now, in our previous tutorial, we said that when capacitors are in series, the charge is going to be the same. Why? Because we said that if this is a positive terminal and we are having this capacitor connected to this side of this terminal, this positive terminal is going to attract electrons from here. When it attracts electrons from here, it means that a positive charge is going to be induced here, since there will be positive charges here. Likewise, this being a negative terminal of this cell, it means that it's going to repel electrons from here, and there will be an excess of electrons on this plate. So it means there will be an excess of negative electrons here. So it means electrons here actually. So it means that there will be a negative charge induced here, and an equal but opposite charge will be induced here. A negative charge will be induced here, and an equal but positive charge is already induced here. So it means that the charge here and the charge there is all going to be the same. So we are required to calculate the charge on C1 and C2, which is going to be the same, and then afterwards we find the PD across each of them. Now the total PD in this whole circuit is 90 volts. So it means that the total PD 90 volts here is going to be equal to the PD across that plus the PD across that. That is for these capacitors in series, just like the way we do it when we are dealing with the resistors in series. So we'll begin with our calculation to try and calculate the charge on these capacitors. Now, for us to find the charge on each of those capacitors, in essence, they're asking us to find the value of Q, and we know that Q is going to be equal to C times V, which is the... So to find the total charge in this whole circuit, because the total charge in this whole circuit is the same charge here, it's the same charge that has been induced here. So the total charge should be equal to the capacitance of the whole circuit, which is the effective capacitance, times the voltage in the whole circuit, which in this case is the EMF, which is 90 volts. Now we so happen to have the 90 volts, which is the V, which is there. So it means we need to first find the effective capacitance in this whole circuit so that we're able to get the charge in the whole circuit. So we begin with our calculations by first finding the effective capacitance. For us to get our effective capacitance, from our derivations before, we said that for capacitors that are in series, 1 over C, which is the effective capacitance, is going to be equal to 1 over C1 plus 1 over C2. And we have one of our capacitors as 3 microfarads, so it's 1 over 3 microfarads, which is 3 times 10 to the power negative 6, plus 1 over C2 is 6, so it is 6 times 10 to the power negative 6 farads. That is going to be equal to 1 over C. So it means that our effective capacitance is going to be 2 times 10 to the power negative 6, which is the same as saying 2 microfarads. So that is the effective capacitance in this whole thing. So now, after getting our effective capacitance, we have our total PDF in the whole circuit, which is 90 volts. So we can get the total charge. And calculating that charge means that we have, it's the same charge for C1 and C2. So it means that our total charge Q is going to be the effective capacitance times the voltage. We got our effective capacitance as 2 microfarads, so it's going to be 2 microfarads. Multiply that by 90 volts, which is our effective EMF. And so our answer there is going to be, this is the same as saying 2 times microfarads is times 10 to the power negative 6 farads times 90 volts. So our answer is going to be 180 times 10 to the power negative 6 coulombs. So that is the charge. So 180 microcoulombs is, in essence, the charge here and in this capacitor, and it's the amount of charge in that capacitor. So it is one key thing that we should all know, that for capacitors that are in series, the total charge in the whole circuit is the same for every capacitor. So we go on to the next part of our question. They're asking us to find the potential difference across each of these. Still, we are going to be basing on this. They want us to find the PD across this and the PD across that. So it means if we make V the subject of the formula, it's going to be V is equal to Q over C. Now, so for us to get the PD across this is going to be V is going to be equal to Q, the total charge which we have already gotten, divided by the capacitance of this capacitor, which is 3 microfarads, and we get our V. We shall do the same story here. So we begin. So for us to get our potential difference across C1, our potential difference V is going to be equal to Q over C. So what is Q? We already got our Q from our previous question. Our Q is 180 times 10 to the power negative 6 coulombs. So it means that it's going to be 180 times 10 to the power negative 6. Divide all that by the capacitance of C1. The capacitance of C1 is 3 microcoulombs. So it is 3 times 10 to the power negative 6. So we end up with 60 volts. So it means that the PD across C1 is 60 volts. What about the PD across C2? Now remember, I said that the total PD, which is 90 volts, for this is going to be equal to the PD across that plus the PD across that for series arrangement. So it means for us to find the PD across this, it is as simple as saying 90 volts minus the PD across this, so that we're able to get the PD across that. So it would mean that PD across C2 would mean it's the total PD, which is 90 volts, minus the PD across that, which is 60. And when we do that, we shall end up with 30 volts as our answer. Or you can still use the same formula here, and you're still supposed to get the same answer. We can still say that V is going to be equal to Q over C, and that's going to be equal to the total charge, which is 180 times 10 to the power negative 6. Divide that by the capacitance, which is 6 microfarads. That's going to be 6 times 10 to the power negative 6. And 180 times 6, we will end up getting our answer being 30 volts. We'll do one more worked example. In this question below, we are being required to calculate the charges on the capacitors and the PD across each. We are having a circuit that is having 120 volts as its EMF. We are having a cell with 120 volts as its EMF. We are having this capacitor being in series with this parallel combination. So if you are to calculate the charges on the capacitor, it would mean that the charge that is in the whole circuit is the same as the charge that is induced in this capacitor, and it is the same charge that is induced on this parallel combination. But first, before we get the charges on the capacitors, on each of those capacitors, let us first find the effective capacitance in the whole circuit. Getting the effective capacitance in the whole circuit means that we have to first find the effective capacitance of this parallel combination, so that we have the effective capacitance of this parallel combination and this capacitance, we combine them and we are able to get the effective capacitance of the whole circuit. So let's first get the effective capacitance of that. We know that these two capacitors are in parallel. So if they're in parallel, it means that for us to get the capacitance of the capacitors in parallel, C is going to be equal to C1 plus C2 plus C3. Parallel combination of capacitors. We did this in our previous tutorials. So it means that to get this effective capacitance for the parallel combination, effective capacitance, let's call it Cy, the effective capacitance here. Cy is going to be 2 microfarads plus the 4 microfarads. And our total answer there is 6 microfarads. That is the effective capacitance for Y, our Cy. So after getting our effective capacitance for Cy, it means that our diagram becomes like this. Right here we have our 120 volts. This is Cy, and it is 6 microfarads, and this is X, capacitance of X, and it is 3 microfarads. So now we go ahead and find, now it means that we have two capacitors that are in series. Now we need to find the effective capacitance of the two. And from effective capacitance for capacitors in series, from our previous tutorials, we said that for capacitors that are in series, the effective capacitance 1 over C is going to be equal to 1 over C1 plus 1 over C2 plus 1 over C3. So for us to get the effective capacitance there, so meaning our effective capacitance, which we shall call 1 over capital C, is going to be equal to 1 over Cx plus 1 over Cy. Our 1 over C is going to be equal to 1 over Cx. What is Cx? Is 3 microfarads plus 1 over Cy, which is 6 microfarads. So when we add up the two, our final answer is going to be 2 microfarads. That is, our question is telling us to calculate the charges on the capacitors. So we go ahead and calculate the charges on the capacitors here. So after getting that, it means we can calculate the charge on each capacitor. Our charge Q is going to be equal to C times V. So the charge in the capacitor, it means we are looking for the charge in the whole circuit, is going to be the effective capacitance in the whole circuit times the potential difference of the whole circuit. So in this case, it's going to be 2 microfarads. Multiply that by the voltage in the whole circuit, which is 120. And so it means that it's going to end up being, we shall end up with 240 times 10 to the power negative 6 coulombs. Now this 240 times 10 to the power negative 6 coulombs is the charge in the whole circuit. So meaning as of this 240 times 10 to the power negative 6 is the charge across Cx, and this 240 times 10 to the power negative 6 is the same charge across the effective parallel combination. So to answer this question here, they're asking us to calculate the charges on the capacitors below. To calculate the charges, so we've got the charges on the charge on Cx. The charge on Cx is 240 times 10 to the power negative 6. Then now, the charge on Cy is also going to be 240 times 10 to the power 6. That is as per capacitors that are in series. But we know that Cy is a derivation of two capacitors that have been in parallel. Now for us to get the charges of these individual capacitors, their total charges combined is 240 times 10 to the power negative 6. But individually, it is actually not the case. Individually, this capacitor has a different charge from that one. But if we sum the two up, it is supposed to give us 240 times 10 to the power 6. But since the question is asking us to calculate the charges on the capacitors, so it means we're supposed to go ahead and find the charge on each of those individual capacitors. So how can we find those charges on each of those individual capacitors? We'll still use Q is going to be C times V. We'll still use that formula. Yes, do we have the Q? This is what we are looking for each of these individual capacitors that are in parallel. Do we have the capacitance of each of these? Yes, this is 2 microfarads and this is 4 microfarads. But do we have the voltage across this combination? We do not know. So meaning that if we set out to find the voltage across this parallel combination, we shall be able to find that voltage across here because it's the same. Multiply that by the capacitance of each of those in each case so that we're able to find the charge in each of those capacitors. Now, take note also that this being 120 volts, this 120 volts is equivalent to the PD across this plus the PD across that. So meaning that if we also know the PD across this capacitor, it's a matter of saying 120 volts minus the PD across that capacitor, and we're able to get the PD across this combination. So now let's get to work and try and find the potential or the PD across X first. So for us to get the PD across capacitor X, which is that one, we know that Q is going to be equal to CV. So it means that the PD across X is going to be equal to Q over C. That is going to be, what is the charge? We already got the charge on that one. We got the charge as 240 times 10 to the power negative 6. So it's going to be 240 times 10 to the power negative 6. Divide all that by the capacitance of that capacitor, which is 3 microfarads, which is 3 times 10 to the power negative 6. And we shall end up getting our voltage as 80 volts. So now that 80 volts, that is the potential difference that is across capacitor X. So if the potential difference across this is 80, it means we can get the potential difference across this combination. It's a matter of saying 120 minus that to get that. So it means that the potential difference across Y, potential difference V across Y is going to be equal to the total PD or the EMF of that cell, which is 120, minus the PD across this, which is 80. And by so doing, we are able to get the PD across this combination, which is 40 volts. So the PD across that combination, because capacitors that are in parallel have got the same potential difference, so the PD across this combination is 40 volts. After getting the PD across the across this combination, so it means you can go ahead and get the charge that is resident in each of these. So to get that charge that is resident in each of that, we know that our value, to answer the remaining part of the question, our value of Q is going to be equal to CV. So to get Q of this first the charge here is going to be the capacitance, which is 2 microfarads. Multiply that by the potential difference across it, which is 40. And by so doing, we are able to get 80 times 10 to the power negative 6 coulombs. That is Q1. Let's call this 1. Let's call this 2. So to get the charge in Q2, it's the same story. We are going to use C times V. Capacitance times voltage. The capacitance of this second one is 4 microcoulombs, for it's 4
microfarads times the voltage, which is still 40, and we shall end up with 40 times 40, which is 160, times 10 to the power negative 6 coulombs. So in so doing, we are able to find the charge in that and the charge in that. So we get the charge on Q1 plus the charge on Q2, giving us 160. This is 80 volts and this is 160 volts. And if you look at it closely, you will realize we got the total charge. Looking at this, the total charge in the whole circuit was 240 times 10 to the power negative 6 coulombs. And we said that this is the same, it's always the same charge for capacitors that are in series. We said that it's 240 in here and it's 240 there. But this 240 is being shared between two capacitors that are in parallel. We have got the charge that is resident on Q1, which is 80 times 10 to the power negative 6. We have got the charge which is resident on 2, which is 160 times 10 to the power negative 6. And if you added these two, 160 plus 80, it is going to still give us the total charge, which is 240 times 10 to the power negative 6. So that is how we do that number, and that brings us to the end of this tutorial. Thank you for watching. If you want to watch more of these tutorials, you can simply subscribe to this channel. For Kisembo Academy, this is Arnold Rangakuramya. Energy stored in a charged capacitor. Now, previously we talked about how we charge a capacitor. And in our explanation for charging a capacitor, we said that when we put a capacitor like this in series with a resistor and we connect an ammeter and we connect this to a source of EMF, we said that this negative terminal is going to repel electrons, and so there will be flow of electrons that are going to be repelled and they'll accumulate on this plate. Likewise, we also said that this positive terminal is going to attract electrons from this plate, and so electrons will be attracted towards the positive terminal, leaving an excess of positive charges here. Now, what exactly happens here is that when these electrons are being repelled towards this plate, they do work against the repulsive forces of the electrons that are already there. Likewise, when this positive terminal is attracting electrons from this plate, from the positive plate, so that they come this way, it is going to, the electrons that are being attracted from here are working against the attractive forces of the positive charges that are already here. Now, that work that is being done by these positive charges against the electrons that are being attracted by this positive terminal, and also the work that is being done against the repulsive forces of the existing electrons here due to these electrons that are coming in, that work that is being done is what is actually being stored in the field, and that work is stored in form of electrical potential energy. So now let us consider a capacitor like this one here. This capacitor has got a capacitance C. It has got a capacitance C, and it has also got charge on its plates. Let's call the charge Q. Now, let's assume that this capacitor has been partially charged. Now, if so, it has been partially charged to a charge, let's say Q. Now, let's assume also now that this charge that is partially has increased slightly by a small charge, which we shall call dQ. Now, if this capacitor was initially charged to partially by Q, and now it has been charged, its charge has been increased by a small charge called dQ. Now, this small increment in the charge is going to involve movement of charge from one plate to another. So, if this change, this small increment in the charge is so small, then we shall assume that
the potential difference across the capacitor has not been affected as a result. So that brings us to this, that if that small increment in charge is so small, then the potential difference can be considered to be unchanged or constant. And by this process, in which case work done will be given by V times that the small change in work that is happening will be equal to the potential difference, which we are assuming that is unchanged, multiply that by the change in Q. Now, where is work done? W is equal to VQ. Where is that coming from? We said that potential difference is the work done per unit charge. Potential is the work done per unit charge. So when we make W the work, the subject of the formula, that is how we end up with this expression, that the work done, the small work, is equal to potential difference times the small increment, or the charge, the small increment in the charge. So now, but for capacitors, we know that potential difference V between the plates is going to be equivalent to Q over C. So it means we are going to substitute for the value of V in this expression. When we substitute this expression in V here, we end up with work done is going to be equal to Q over C. So now, if the total work done for that increment, it is so it means we are going to, now if we are talking about a small increment in the charge. Now what if this increment in charge, let's say the capacitor was previously having no charge, so meaning it's having 0 charges, and then it was full, it was charged to full capacity, maybe it was charged to value Q. So for us to be able to find the work done in charging that capacitor from 0 up to Q, which is when it is at full capacity, it means we are going to integrate this expression here with respect to Q, and our limits will be that we are charging this capacitor from 0 up to Q, and then we will be able to find the work done in charging a capacitor fully. And in integrating both sides of this expression, we shall be able to find the expression for work done. So work done W in increasing charge from 0 to Q will be this. So the work done is going to be V times dQ, and in the place of V we substituted Q over C, because V is equal to Q over C for capacitors, times the change in Q. So meaning we are going to integrate this expression with respect to Q, with our limits being we are charging the thing from 0 up to Q, up to charge Q when it is fully charged, and the work done is from 0 up to W, work done. So integrating will give us work done being equal to 1 over C. Since we are integrating with respect to Q, it means it's going to be 1 and C are constant, so we bring them out of the integral sign and we only integrate this. So it's going to become, integrating this, it is to the power 1. So for us to integrate, it's going to be, we are going to add 1 to the numerator, and the answer we get here, we divide by the whole term, and we'll end up with our work done for being Q squared over 2C. That will be our first expression for work. Now if we are to substitute the value of Q, remember for capacitors, the charge Q is going to be equal to the capacitance times the potential difference. So Q is equal to CV. So if you are to substitute for CV in this here, so that work becomes CV, C squared V squared over 2C. We'll end up with another expression for work done, which is W is equal to CV squared over 2. That's our second expression. Then also if we want to substitute for the value of C, you know C is going to be Q over V. If we to substitute for the value of C here, it would mean that we'll come up with another expression for work, which is going to be QV over 2. So those three are our three expressions for work. The first one, the second one, and the third one. Those are our three expressions for work done in a capacitor. If you want to watch more of these videos, simply subscribe to this channel, and for the benefit of your colleagues out there who would like to watch more of these tutorials, simply share this video. Otherwise, thank you for watching and hope to catch you in the next tutorial. For Kisembo Academy, this is Arnold Rangakuramya. Joining two capacitors. Today we get to look at what happens when we join two capacitors. The diagram on your screen is showing capacitor C1 and capacitor C2. When we close switch S, these two capacitors are joined together. Now, we might have a capacitor C1 having a certain amount of charge on its plates. We are having a capacitor C2 having a certain amount of charge as well. When we connect these two capacitors, if we are having a capacitor with a higher potential difference than the other, it means charge will flow from the plates that are having a higher potential difference towards the capacitor whose potential difference is low. And charge will stop flowing when the potential difference across these capacitors becomes the same. In other words, these two capacitors have been connected in parallel. They've been connected in parallel, and when we connect them, charge will flow from a capacitor with a higher potential difference to a capacitor with a lower potential difference. And when it so happens, it does so to the point that the potential difference across C1 and the potential difference across C2 becomes the same. So when that happens, charge stops flowing. Now, the final potential difference and the energy of each capacitor will be calculated. We shall calculate this in our worked example that we are about to do. But the three things we should put in mind here are that, one, that these capacitors, first of all, have been connected in parallel. And then the other issue we need to put in mind is that for this charge that has been flowing from one capacitor to the other to stop flowing, it would mean that the potential difference across this capacitor and the potential difference across that capacitor have been the same. In other words, what we are trying to say here is that the charges flow so that they normalize the potential difference. Then also we'll be able to see that the energy that was stored initially and the energy that is stored after the two capacitors have been connected will be different. It will be less. Now, why is that so? Because when this charge is flowing, for example, when charge is flowing from one capacitor to the other so that the potential difference across both capacitors is normalized, as that process is continuing, some of the energy is dissipated as heat in these connecting wires. So that energy that is dissipated as heat in the connecting wires as charge is flowing is what is responsible for the decrease in stored energy after we connect the two capacitors. We'll look at a worked example to demonstrate this further. A 5 microfarad capacitor X is charged by a 40 volt supply. It is then connected across an uncharged 20 microfarad capacitor Y. They're asking us to calculate the final potential difference across each, the final charge of each, and the initial and final energy. This is the capacitor we're talking about. It is having a capacitance of 5 microfarads. Now, a 5 microfarad capacitor X is charged by a 40 volt supply. So it means it has been charged by a 40 volt supply. And it is then connected across an uncharged 20 microfarad capacitor. So this is 5 microfarads. It has been charged by 40 volts. Now we are charging this capacitor we shall call C1, and we are connecting it to another uncharged 20 microfarad capacitor we shall call Y. So this thing was initially 5 microfarads and it's charged by 40 volt supply. So we'll call it, this is a 5 microfarad capacitor. It has been connected to an uncharged 20 microfarad capacitor. So this is the 20 microfarad capacitor. This is a 5 microfarad capacitor. It has been charged by a 40 volt supply. Now we get this 5 microfarad capacitor that has been charged, and we have connected it to a 20 microfarad capacitor which is uncharged. So what happens? What happens is that charge will flow from this capacitor to this, and the reason as to why it will flow is so that the potential difference across this capacitor and that capacitor is normalized. When the two potential differences now become the same, then charge will stop flowing. So now they're asking us to calculate the potential difference, the final potential difference across each. Now we know that the final potential difference across this capacitor and that capacitor will be the same. So we set out to start calculating it, and so we get to work. Now for us to find the final potential difference, we know that V is going to be equal to Q over C. So for us to find the potential difference, the potential difference across each capacitor, we need to find the total charge in the whole circuit, and we also need to find the effective capacitance in the whole circuit. Now remember, we do not know the effective capacitance, we do not know the charge, the total charge in the system. So before we find V, we need to first find Q, we need to first find C. But remember, before this capacitor was connected to this one, which is not charged, this thing had been charged. C1 had been charged by a 40-volt supply here. So meaning that for us to find the total charge in this whole system, we need to find the charge that is resident in the 5 microfarad capacitor when it had been charged by the 40-volt supply, because it is this charge that was brought into this circuit with this not having any charge. So since this didn't have any charge, it means that the total charge in this whole circuit is the charge that had been charged by these 40 volts. So to first find that charge, we know Q is going to be equal to CV. So our capacitance here is 5 microfarad, so it's 5 times 10 to the power negative 6. Multiply that by the voltage that was charging, which is 40. And we shall end up with 200 times 10 to the power negative 6 coulombs. So mean we have our value of Q, it is 200 times 10 to the power negative 6 coulombs. So now we need to find the effective capacitance in the whole system. Now these are two capacitors in parallel. Since there are two capacitors in parallel, it means the effective capacitance is going to be equal to, effective capacitance will be this plus that. So it's going to be C1 plus C2, and that's going to be 5 microcoulombs plus 20 microcoulombs. And our answer here is simple. It is going to be 25 microfarads. So it's going to be 25 microfarads. That's the effective capacitance. So after finding the effective capacitance, so we can go ahead and find the potential difference across each capacitor. So the potential difference therefore across each capacitor is going to be the charge, which we already got as 200 times 10 to the power negative 6 microcoulombs. Divide that by the 25 microcoulombs. So it's 25 microcoulombs. It's 25 times 10 to the power negative 6. It's microfarads. I keep making that error. So it's microfarads, and here it is 200 times 10 to the power negative 6 coulombs. And so meaning from there we shall get our final answer as 8 volts. We have answered part A of the question, the final PD across each. So it means that when we connect those two, the final potential difference across each capacitor is 8 volts. So we'll go ahead and find the final charge on each capacitor. So for us to calculate the final charge on each capacitor, the final charge Q, we know that Q is going to be the capacitance of each capacitor. Multiply that by the potential difference across each capacitor. We know that the potential difference across each capacitor is 8 volts, and we know that each capacitor has got its own capacitance. So to find the charge on each of them, remember the charge redistributed itself in an effort to normalize the PD across each. So Q1, the charge across capacitor 1, we know that capacitor 1 has got 5 microcoulombs, so it's going to be 5 microcoulombs. Multiply that by the PD, which is 8, and we'll end up with 40 microcoulombs. Then the charge across capacitor 2, which is still going to be C times V. The capacitance of that is 20 microcoulombs, so it's going to be 20 microcoulombs times 10 to the power negative 6. Multiply that by the potential difference, which is 8. Capacitance for C1 is 5 microfarads, not microcoulombs, like I had said earlier. Excuse me for that error. And we shall end up with 160 microcoulombs. And if you will see, when we add up 160 microcoulombs plus 40 microcoulombs, it's going to give us 200 microcoulombs, which is the total charge in the whole system. So that is, we've answered Roman 2 of the question. Find the final charge on each. So Roman 3 of the question is requiring us to find the initial and final energies in the system, in the two capacitors that had been connected. Now we know that the initial energy, let's call that U, or the initial energy is the same as the work done. It is going to be equal to a half CV squared. We derived these equations in the previous tutorial. So initial energy is a half CV squared. Now the initial energy is the energy that was contained by that capacitor C1, which was charged. This one was uncharged, so it didn't have any energy in it. This one had been charged by 40 volt supply. So that is, so we calculate the initial energy of that one. The initial energy is this that had been charged by the 40 volts, this capacitor that had been charged by the 40 volt supply. So the initial energy that was maintained here, contained here, which was brought into this system, which was when this capacitor was connected to this that had not been charged, is going to be equal to a half times the capacitance of that, which is 5 microfarads, 5 times 10 to the power negative 6. Multiply that by the voltage across the combination, which is 40. And our initial energy there is going to be 4 times 10 to the power negative 3 joules. That's our initial energy. Now let's calculate our final energy, because the question is asking us to initial and final energies. So what is our final energy? Calculating our final energy means you're going to find the energy that is possessed by the first capacitor C1 when it had been connected, plus energy in C2. So final energy is going to be a half times C1 V squared plus a half times C2 V squared. So that's going to be a half times our first capacitor, which is that, times 5 times 10 to the power negative 6, times V squared. The potential difference across this is, remember when we closed, the potential difference, when charge flew, the potential difference across the two became 8 volts. So it's going to be times 8 squared plus a half times C2. C2 is 20 microfarads times 20 times 10 to the power negative 6 times 8 squared. So we'll end up with the total energy being 0.8 times 10 to the power negative 3 joules. So we have answered this question, the initial and final energies. If you look at our initial energy, it is 4 times 10 to the power negative 3 joules. Our final energy is 0.8 times 10 to the power negative 3 joules. Now, why is it that our initial energy is higher than our final energy? At first, we got a 5 microfarad capacitor. We charged it with a 40 volt source, and it acquired, when we charged it, it acquired our initial energy, which is 4 times 10 to the power negative 3 joules. And now, we get this 5 microfarad capacitor, and we connect it to another capacitor, which is a 20 microfarad capacitor. But this 20 microfarad capacitor that we have connected to this capacitor was initially not charged, meaning it didn't have any energy that it was storing. So what happens? What happens is that charge flows from this capacitor to that capacitor until the potential difference across these two capacitors becomes the same. And when the potential difference across these two capacitors becomes the same, in our calculations we find that actually the potential difference now becomes 8 volts across that, and it is also 8 volts across this. So when we go ahead and calculate for the final energy that is stored in this system, we find that the final energy is 0.8 times 10 to the power negative 3 joules, which is a bit less than the 4 times 10 which was initially there. So now the explanation for this is that the energy dissipated as heat in the connecting wires when the charges flow from the 5 microfarad capacitor to the 20 microfarad capacitor accounts for the decrease in the stored energy. Thanks for tuning in. For the benefit of your colleagues out there that would like to watch this tutorial, simply share this video. For Kisembo Academy, this is Arnold Rangakuramya. The parallel plate capacitors, one with air and the other with mica, are identical in all aspects. The air capacitor is charged from a 400 volt DC supply, isolated and then connected across a mica capacitor, which is initially uncharged. The potential difference across this terminal combination is 50 volts. So assuming that the relative permittivity of air is 1, calculate the relative permittivity of mica. Now the question here is they're asking us to calculate the relative permittivity of mica. Let's ask, what is relative permittivity? We remind ourselves, first of all, relative permittivity is the ratio of the capacitance of a capacitor with the dielectric between its plates to the capacitance of a capacitor without the dielectric between the plates. That is the definition for relative permittivity. So it means for us to find the relative permittivity of mica means that we need to get the ratio. It is as simple as getting the ratio of the capacity of the capacitance of the mica of the capacitor with this mica to the capacitance of the same capacitor without the mica in between. That means with a vacuum in between its plates. So let's get started. We interpret the question in a with a diagram. We are having two capacitors here. They're telling us that the parallel plate capacitors, one with air, we are calling one with air CA, A standing for air. One with air and another with mica. So one with air we are calling it CA, the other one with mica we are calling it CM. So now, these are parallel plate capacitors, one with air and the other with mica. They are identical in all aspects. If they are identical in all aspects, it simply means that they are having the same capacitance. Okay, so the air capacitor is charged from a 400 volt DC supply. So this is, before this connection took place, this air capacitor was charged with a 400 DC supply, and it isolated and then connected across the mica capacitor, which is initially uncharged. So this mica capacitor here initially does not have charge, so we get this capacitor of this air capacitor that has been charged from a 400 volt DC supply, and it is connected in parallel with a capacitor with the mica as a dielectric, which we are calling a mica capacitor, which is initially not charged. So the PD across the terminal combination becomes 50 volts. So meaning after connecting this to that, the charges from here flow to this. When the PD eventually normalizes and the charges stop flowing, the potential difference across this capacitor and that capacitor is said to be 50 volts. Now they're asking us that, assuming that the relative permittivity of air is 1, calculate the relative permittivity of mica. So we get to start working now. Now, when they say that the relative permittivity of air is 1, it means that the relative permittivity of air is, remember, relative permittivity of air means it is the ratio of the capacitance of the capacitor with air in between its plates to the ratio of the capacitance of the capacitor when there is nothing, when there is a vacuum in between the plates. So it means in this case it is going, let's call that CV. So the relative permittivity of air, which is the ratio of the capacitance of the capacitor with air in between to the capacitance of the capacitor when there is nothing, we've called it when there is a vacuum, when there is nothing, is equal to 1 according to the question. So meaning that this expression is same as saying 1 is equal to capacitance of the capacitor over capacitance of V. So when we multiply CV on both sides, it would mean that CA is the same as CV. So they're asking us to calculate the relative permittivity of mica. So calculate the relative permittivity of mica. We also know that relative permittivity of mica is going to be equal to the capacitance of the capacitor when there is mica in between to the capacitance of the capacitor when there is nothing. We shall call that CV when there is nothing. This was charged by 400 volt DC source. Then it was connected to this uncharged capacitor. So it means that all the charge that was generated here is what is here. The total charge here, meaning, is going to be equal to the charge in the capacitor that has got air in between its plates plus the charge that has got mica in between its plates, because when we get this capacitor and we connect it to this one, the charge that had been accumulated here is redistributed between these two, and the total charge here is the same as the charge that was accumulated here during this charging. So we'll begin from that angle. So the total charge here, which we are going to call Q, is going to be equal to the charge that is in the air capacitor plus the charge that is in the mica capacitor. Now the total charge in this whole combination is the charge that was accumulated when this air capacitor was being charged, because remember we got this air capacitor, connected it to this mica capacitor when there was nothing, no charge in this one. This was initially uncharged. So it means that all the charge that had been accumulated by the air capacitor when the 400 DC source was charging it is the same charge, the total charge in this whole system. So it means that the total charge before connecting is going to be equal to the total charge after connecting. So the total charge before connecting, which we have called Q, is going to be equivalent to CV. It's going to be CA times V is going to be equal to the charge that is in the air capacitor after connecting, which is going to be CA times V plus the charge, the total charge in the capacitor of the mica capacitor after connecting, which is we are calling CM times V. So we continue with our calculation. We know that CA here before connecting, CA is remaining as it is. It's going to be CA multiply that by the potential difference, which is going to be 400. Is going to be equal to CA times V, which is CA times V. Now the potential difference after connecting, according to the question, says that it is 550 volts. So it's going to be times 50 plus the capacitance of the mica, multiply that by 50. So we end up with 400 CA giving us 50 CA plus 50 CM. When we divide through by 50, so when you divide through by 50 by 50 by 50, 8 CA, this by 50 once by 58, so it means that 8 CA is going to be equal to CA plus CM. When we make CM the subject of this formula, we'll end up with 8 CA minus CA giving us 7 CA. So the capacitance of mica is equivalent to 7 CA. But then the question here is requiring us to find the relative permittivity of mica. And we said for us to get the relative permittivity of mica, is going to be equal to the capacitance of the capacitor when there is mica in between the plates to the capacitance of the capacitor when there is nothing. We've called that CV. So now, according to our calculation here, we have gotten our value of the capacitance of the mica is equivalent to 7 CA. So we can go ahead and say it is 7 CA, divide that by the capacitance when there is nothing, CV. But then, from our information, from our question, we were told that the relative permittivity of air is 1. And we said that when relative permittivity of air is 1, we said that we ended up with an expression that CA is going to be equal to CV. So if we are having CV here and that same CV is going to be CA, it means that this can also turn into CA. So this is going to end up being 7CA, divide that by CA. When that cancels out, we remain with the relative permittivity of mica being 7. And that's our answer. That brings us to the end of this tutorial. Thanks for tuning in. For the benefit of your colleagues out there that would like to watch this tutorial, simply share the video. Otherwise, for more of these videos, I encourage you to subscribe. For Kisembo Academy, this is Arnold Rangakurami.